Hello. Hi, Fernando. Can you hear us? Nice to meet you again.
Should I try the share the document? Just
Yeah. Hi, Fernando.
hello.
Yes. Yes, please.
So I can start sharing the document.
Yes. Please share your screen. Okay. Are you ready to start?
Yes, anytime. Yes.
Okay. So we probably can start. So the lecture is 15 minutes plus 5-minute questions.
Okay.
Okay. Please take seats. So we are very happy to have Professor Fernando Quevedo from Cambridge University and SR. And Professor Quevedo is a leading expert in string theory, and in particular, string cosmology. He's going to give us 2 lectures today and tomorrow online. The title of his lectures is String Theory and Cosmology. Let's welcome him.
Well, thank you. Thank you very much, Jun. So, well, thank you for the invitation to participate in this school. And I'm sorry I couldn't join you in person, but I'm very pleased to be able to give some lectures by Zoom. So the title is String Theory and Cosmology. Is very broad, so in that sense, I will try to be as explicit as possible. But just to let you know that we have let me see if you can see the pointer here. Well, there are these 2 recent reviews that I wrote, one in string and cosmology, together with Michele Ciccoli, Joseph Conlon, Anshu Maharana, Susha Parameswaran, and Yvonne Zavala. It appeared earlier this year in Physics Reports. So that's a very comprehensive, probably the most up-to-date review on the subject. So I will encourage you to look at it. You want to see more details of what I'm talking today, because it's a very comprehensive subject. So there are many things that I will not be able to cover in detail. So all the details will be in that review. But also a big component of cosmology and string theory is the subject of moduli stabilization. I will tell you what it is later on. But I also wrote a review that appeared also this year with Liam McAllister in the Handbook of Gravity, but I gave you the archive number. So that is a much more technical review that gives all the details about moduli stabilization, which is the most important question that is still being addressed at the moment, because it is without moduli stabilization we cannot make contact of a string theory with cosmology or even with any other aspect of physics. So I also encourage you to take a look at this review. It is appeared in the archive last year, but it was published this year. Okay, and you have any questions or comments at some point, please interrupt me and I would be happy to discuss. And can you hear me well? Yes? Okay. Very good. So let me start from scratch. So we all know that we have the standard model of particle physics, which is a very well developed theory with a very solid background and well founded. There is also something people call the standard model of cosmology, which is not that well founded, is not that solid. It's called lambda CDM. Lambda stands for the cosmological constant, and CDM for cold dark matter. And essentially, looking at the equations, I'm sorry I don't see the pointer here. For some reason, the pointer. I don't see how. Anyway, so I'll try to see it in the. I try to just say the words because I don't see the point. So the cosmological constant is the standard Einstein's equations with the r mu nu minus 1/2 g mu nu r plus lambda g mu nu. That's extra term he added to the equations at that time to get his theory to be consistent with the static universe. But as you may know, in the last 20 years or so, there's evidence that there is something like the cosmological constant that is positive, and extremely small, and that's one of the big mysteries of our time. And it may be just a constant, or maybe a varying field or so. We still don't know, but essentially, the standard model of cosmology, just putting lambda to be a constant, fits very well with experiments. And as it says there, lambda equal to 0 is Minkowski spacetime, the flat spacetime. Lambda is positive is de Sitter spacetime, and lambda negative anti-de Sitter spacetime. Experimental evidence is that lambda is of order 10 to the minus 120 in Planck units, and Planck units means units of the Planck scale, which is the scale that we can define by using the fundamental constants of nature, including quantum mechanics, h bar, relativity, c, and gravity, g. And that scale is 10 to the 19 GeV. And so the evidence for lambda is something extremely small, 10 to the minus 120, that number, and that's the big challenge to understand. But taking it for given, just put that number, fits very well with experiments. And the other component of that is called dark matter. It's a new kind of matter in the sense that it's not made of baryons or photons or neutrons and so on. It is dark in the sense that it's electrically neutral. And it's cold. That means that they move with a velocity much lower than the speed of light. So that means that the matter cannot be just a photon or a neutrino, which is very light and will move fast. And with like any other matter, it is gravitationally coupled. So it may be also weakly coupled, but at least definitely it's not gravitationally coupled. And it cannot be a strong nor electromagnetic coupled. So that's the term dark matter. And that component makes a big percentage of the matter content of the universe. And a big part of the whole energy share of the universe. Lambda, the cosmological constant, makes most of it, so more than 70%, and then the dark matter also make the rest. So essentially, that's the general picture. So the important thing here is that I want to emphasize that it is a model that fits the experiments, but there is no underlying theory behind it. You just write the questions or answer the questions, put a lambda, and put some matter that we don't know what it is, and things fit very well with the experiments. But the mystery is to identify what this cold dark matter is, and to identify what is the source of this cosmological constant or any variation of it, and why it's so small. Okay, so having some technical problems to move the slide. For some reason it's not moving now. I'm afraid I will have to stop for a second the sharing, because this is. Okay. Sorry, that was important. Okay, so open problems in theoretical cosmology. So we know that you extrapolate on time with the universe accelerating and expanding in general, and you extrapolate back in time. We have to address the what happened at the Big Bang, where most of the matter of the universe is concentrated in a very small size, and we don't know, we cannot describe the Big Bang at the moment. There is a theory of inflation that explains many of the problems with the Big Bang, and we have to understand what is the origin of inflation or alternatives. The important thing is that this inflation that this provides is that the big evidence of the Big Bang is that this cosmic microwave background that has been seen since the 1960s, and the fluctuations of the background has been observed in the last 25 years. And the origin of those fluctuations is inflation provides that origin, but there may be another theory that could do it also. So that's something to keep in mind, and that's an open problem. So there are models of inflation, but none of them have a fundamental origin. So it's people just putting them by hand. So the question is how to derive inflation from a fundamental theory. The same thing is how to, as I said before, how to derive dark energy or dark matter from a fundamental theory. And baryogenesis, which is why we are made out of particles and not antiparticles. And so all of that, it is we need to understand that because there is a lack of an underlying theory, and that's what subject of this lecture will be, because that's what string theory will try to do. I can warn you already that it's not totally successful, but progress has been made in the last 25, 30 years, and but that is the motivation for this. So there are these observational successes of cosmology, which is now the greatest time for cosmology and observations, because it's becoming a theory which is a very precision cosmology, and we have a lot of data, and so the challenge is the theoretical part, how to understand that data. And to the minus 120, as I told you before, and there's this W, which is the essentially the equation of state, pressure over density, and which is very close to -1. If it were -1, exactly -1, there will be this dark energy will be a cosmological constant, but it's slightly different from -1 up to the error, so there's room for something else, but it's very, very close to being just a cosmological constant. Okay, so strings and cosmology, so string theory will try to address this question, and so I can separate it in several parts, which I will organize my talks on this. One is the Big Bang, put a question mark. Nothing to be said at the moment. We don't have anything to unfortunately, the theory is not well developed to even address the Big Bang question. But still, we can address inflation or what happened before inflation. And so that's one aspect. The other one is inflation, how to derive inflation from string theory. The next one is what happened after inflation. And after inflation is when you have what you produce most of the matter of the universe, and that will be the thing that is called reheating or preheating, and then you'll get dark matter, baryogenesis, etc. Everything after inflation. So we have to find a stringy origin of that. And then today we have to explain why cosmological constant or whatever dark energy is so small. And of course, we can inquire what will be the future. Having the string theory, if string theory can tell you something about the long-term future. So I will address mostly the points in red, the before inflation, reheating, and dark energy, but also I will mention models of inflation coming from string theory. Okay. So then we start with string theory. And string theory is it's a vast subject. I cannot summarize it in a slide or a few slides. So let me just tell you roughly that the summary of this table that I have here. We have 5 different string theories: heterotic E equals C8, heterotic SO32, and type 1, so 32, type 2A, type 2B, and a sixth theory called M theory that it lives in 11 dimensions, whereas the other one's in 10. The string theory, of course, is the typical picture that you start with the strings moving in some background space-time, and they can interact with each other, and the oscillations of the strings will give you different particles. So, important thing is that the critical dimension for strings is 10, or if you go to M theory, you go to 11. This is always supersymmetry, which is symmetry relating bosons to fermions. And the relevant things for low energy, as we are now, or to describe backgrounds and so on, are the massless states. And the massless states, the bosonic ones are the most relevant. And then you can see each of these theories have a massless states, which is GMN, which is a symmetric tensor, a two-index symmetric tensor. And that's the metric that describes gravity. And that's behind the statement that people say string theory predicts the existence of gravity, because all of them have a state, a massless state, which is a symmetric tensor of rank 2 tensors, which is symmetric, and that describes the graviton. I mean, it's a particle of spin 2 and massless. And that's what we want, and that's very good. But it also describes other things. If you look at the first row, there's heterotic it describes, and the second row is AMIJ. Those are vectors. M is a vector, and Ij are internal indices, and those are like gauge fields that describe that could eventually incorporate the standard model ratio 3 cross 2 cross 1. So in that sense, that's also we wanted. And so some of them have it and some of them not, but essentially there. But there are other objects, the BMN and the phi. Phi, you can see in all the string theories, well, not in the M theory, but all the string theories. That's a particle called the dilaton. That's very important. We didn't ask for it, but string theory predicts that particle. And the important thing is that the expectation value of the dilaton gives us the strength of the coupling, the string coupling. So string theory doesn't have free parameters, only the scale. And all the couplings should be vacuum expectation values of fields, and the dilaton give you the important one. Give you the is there any question? No? Okay.
No question.
Sorry, I hear some voice. No?
No question.
Okay. Okay, thank you. Very good. And well, then there are these objects which are less common, which are the antisymmetric tensors, BMN, that appears in most of the string theories, is essentially is an object with two indices, and then actually couples to an object which have two dimensions, which will be like the string theory bullshit. So that's a natural thing to couple to strings in the same way that electromagnetic fields couple to particles. And then there are other ones like CMNP in the type 2A and CMNPQ in type 2B and so on. That sort of antisymmetric tensors of different indices that in 4 dimensions don't mean that much because they're always equivalent to something we know. But in higher dimensions, they're objects by themselves. And they play a key role in 2 ways. One is that they can be sources of fluxes, like a magnetic fluxes or so. Because they are more essentially generalizations of gauge fields, just with more indices, but they can also couple to extended objects in the same way that, as I say, a particle couples to a gauge field and a string couples to a BMN, something with that couples to CMNPQ, it can be it's called a brane, a D-brane of dimension 3, so D3 brane. So in that sense, these new objects give you these new tensors give you new perspectives in the theory, and that will give you things that will play a role in the physics. And one, as I say, is the fluxes, and second is the existence of extended objects like D-branes. Okay, so essentially that is the structure of string theory massless states. and they're the ones who can be considered for backgrounds. I emphasize that the theory is unique. All of these 6 theories that I told you in the 90s were proven to be equivalent to each other by the different dualities. So in that sense, the theory is unique. There are no free parameters. And also, there are no free parameters. So in that sense, it is what you want for a theory, for a fundamental theory to have. A string theory provides you that. So it's a unique theory with no free parameters. And then the rest you have to explore with this information, what is the physics that you can extract. Since they all start with 10 dimensions, so we have to go to lower dimensions. You have to compactify. And so that means that 4 of the dimensions will be ours, and the extra dimensions can be objects like this manifold here, which is called Calabi-Yau manifold. And that will be 6-dimensional with a very complicated topology, and that's what makes a very rich contact with mathematics and string theory. And then these objects that I told you before, brains, can exist there, and then you can have here one brain wrapping one of the non-trivial cycles and extending, and that will be one universe. On the bottom left, you can see that object like a brain. Like I put something like looks like the universe. That could be our universe. That would be a brain in these extra dimensions. So covering our dimensions, and the whole manifold that I showed you there is this extra 6 dimensions. And then the 2 objects in red, one is wrapping around. That would be a 7 brain wrapped in 4 cycle, or a 3 brain in a singular point. So that is a typical compactification. You have to start with the 10 dimensions and look for solutions that are of the theory that give you the 6 dimensions, which are small, with all different objects there. And then we can be living in one of these objects, in one of these brains. Okay, so that is the general picture of compactification that people have been developing over the years. So to give you more concrete questions, you can start with one of the string theories. They are all equivalences, but some of them are more convenient than for some questions. So type 2B happened to be a very relevant for describing this compactification. So I will concentrate on that one. So you start with an action, like the integral of the Lagrangian. And then the first term, root GR, is the standard Einstein term. But then you have the kinetic terms for other fields. So the big tau or imaginary of tau square, where tau is C0 plus I e to the minus phi. I told you C0 is one of these antisymmetric tensors, but in this case has no indices. So it's an axion of particle. And then G3 is a combination of F3 and H3, which each of them are derivatives of 2 forms that appear in the spectrum that I showed you before. And then the last term is a topological term, the Chen-Simons term, with C4, G3, and G3 bar. So you start with that axiom, that is an effective field theory. And the question is, starting from that, look for solutions. So effective field theory in 10 dimensions, look for solutions that will give you 4 dimensions. And then you have to split the metric into the G mu nu, dx mu, dx nu, that's the 4-dimensional part, plus GMN, dym, dyn, which is the extra dimensional part. And then look for solutions. The solutions of Einstein's equations. Then you put the R mu nu, where mu and nu are the 4-dimensional indices. That will give you equal to 0. That will give you flat space-time. And then Rmn also give you equal to 0. And that will not be flat dimensional extra dimensions, but that will be an extra dimensions which are Ricci flat. So the Ricci tensor Rmn is 0, but not the whole curvature. So these Calabi-Yau spaces that I was showing you in the picture before are precisely those kind of spaces where the Ricci tensor is 0, but you can see it's a very complicated and curved space. Okay. And when you solve that, what you get is that you get a lot of flat directions in your potential. So that means fields, scalar fields, which are have a potential which is 0, so just flat. And those are called the moduli fields. And that's, let me just tell you more detail of the moduli fields. You start with, for instance, you start with the 10-dimensional metric, G capital Mn. and you split it into the 4-dimensional part and a 6-dimensional part. The G mu nu will have the that will be the metric in our 4 dimensions that will describe our standard gravity. The G mu n will have an index mu, which is space-time index, plus an extra index n, which is the extra dimensions. So in 4 dimensions, you will be seeing as many vectors, G mu's with labeled by n. And then in the top diagonal and the bottom diagonal part, you have the GMN, and GMN, since they don't carry space-time indices, 4-dimensional space-time indices, there are a bunch of scalars seen from the 4-dimensional point of view. Okay, so this bunch of scalars, they measure the size and the shape of the extra dimensions because gravity is essentially related to space-time. So these are what's called the moduli. So in the question you found, these fields can have any value. And so that means there's no potential to be determined. And there are many of them depending on the topology of the corresponding manifold. So, so to have your mind in the simplest way is that imagine the extra dimension, you have only one extra dimension. This model will be the radius of the circle. So if it is a circle, the extra dimension is a circle, this will be the radius of the circle. And the equations of motion are such that they are solved for any values of any value of the radius of the circle. And that was an issue that was proposed already 100 years ago by Caruso and Klein. They proposed, oh, we have an extra dimension, a circle, and we don't know how to fix it. But let's assume that it's small in such a way that we don't see it. So that's the standard picture. So why is it that we don't see the extra dimensions? Because they are too small for us to see. However, we have to explain why they are so small. It has to be derived from the theory why they are so small. But if they are free parameters, that means that any value is possible, and that's the problem. That is the moduli problem. How to fix this size of the extra dimensions. And that brings me to the string landscape. And the string landscape essentially is something that has been developed in the last 25 years or so, just addressing the question of moduli stabilization. So how to fix this moduli. And I remind you that that's all the texts are in this review that I wrote with Lee and McAllister some time ago, last year. Okay. So let me just try to give you a rough picture of this. So you have the point that you have this complicated manifold that I told you with a lot of non-trivial cycles. And if it is 6-dimensional, the 6 dimensions has non-trivial cycles of the lower dimensionality. So you have a non-trivial 3 cycle and the dual, 3 plus 3 is 6. And you have and those are called complex structure moduli. And then you have non-trivial 4 cycles and their dual 2 dimensions, and they're called the Keller moduli. There are no 5 and 1 cycles for these manifolds, in particular related to the fact that they don't have isometries, for instance. So, so essentially, and the sizes of those cycles are part of this moduli. So in that sense, those are the ones you have to determine. The Keller moduli are usually called T, the complex structure moduli are usually called U. And on top of that, there's the dilaton that I was calling it tau before, now I'm calling it S for some reason. Okay, so we have U, T, and S, and they're all modular, they all have flat potentials, and we have to find ways of generating potentials for them to be fixed. Okay, so just to put you in perspective, there are 3 related questions that we want to address thinking about the physics. One is moduli stabilization. So we want to find the size and shape of these extra dimensions. Okay, so just to see if we can claim that they are small extra dimensions, and that's why they are not observed, for instance. But also we want to get the zeta space. We want to get a cosmological constant, which is positive and non-zero. And that is the second row in my picture. The zeta means that you have a potential, and at some point, the potential is not flat, it has a shape. The shape is such that you have a minimum, and the minimum is at the value of the energy, which is positive, and the cosmological constant will be proportional to that energy. That's it. So, essentially, the cosmological constant is the energy of the vacuum. So what we are looking for is that stabilizing the moduli. Stabilizing the moduli means that you have to find a minimum, and that's the minimum. But now the minimum cannot be any minimum. We want it to be a minimum such that it will give us a positive cosmological constant, because that's what we observe in nature. So that's the challenge. And on top, the third point is to get inflation. What is inflation? Inflation, at the end, you need a potential such that early in the universe, the potential has a positive vacuum energy, but big vacuum energy. And that, since the vacuum energy is large, so that will be like almost a cosmological constant, that it will be large. What it will cause the universe to expand exponentially, very fast, much faster than now. Now it's expanding exponentially, but since the cosmological constant is so small, the expansion the acceleration is small. But inflation is a real big acceleration at the beginning of the universe to address all the problems of the original Big Bang, related to the horizon problem and flatness problem, and so why the universe is so flat, etc. And that field, the scalar field, so you need to find then the potential, not only to give you a minimum with a small cosmological constant, but also to have a region where you can have almost cosmological constant at very high energies. And that is what is called a slow roll. There's potential which is rolling very, very small. It cannot be just a constant, because the universe will continue accelerating, and never get to the time that we are now. So it has to come to the level that we are now. So we want to have potentials like of this type. A minimum with a positive cosmological constant, and a region where you have a slow roll potential. Okay? And that will give you inflation, and then in the early universe, and then now the sitter in our universe. So essentially, that's the challenge. So people have been putting these potentials by hand when people talk about inflation and so. The challenge for string theory is to derive these potentials. So the three questions are related, because the original question is, we want to stabilize the moduli, but now you have to refine it and add two extra terms. You want to stabilize it to get the sitter, so not any minimum, but the minimum which is positive. And not only just getting the sitter, but getting a region that gives you inflation at early universe. So you want the potential, like the third figure in this plot. Okay, so that is the challenge that any theory has to address. If you want to derive inflation, if you want to derive it from fundamental theory. Okay. So I told you the potential for these fields are flat in general. So how can we generate a potential which is non-flat? Now the fluxes can play a role. So these fluxes that I told you, the antisymmetric tensors that are similar to magnetic fluxes. So it will be like something fluxes around one of the non-trivial cycles. And if you call capital R a typical size of the extra dimensions, we know that the fluxes will give you a source of energy, because the flux is going around one of the cycles, and that will give you a potential energy of the order of r to the minus 6 minus 2p, where p is the dimensionality of the corresponding cycle. So the cycles that are non-trivial. Also, you have branes, as I told you before. They carry energy because they have tension, and that will give you r to the p minus 15 for a p-dimensional brane. If the manifold will have curvature, I told you the Calabi-Yau manifolds don't have curvature, don't have Ricci curvature, and then the scalar curvature is also 0. But there may be other manifolds for which they have curvature, and then that will contribute the potential to the form 1 over r to the 8. And you have, as I told you, the potentials for this fields are flat, and that's a statement at tree level in perturbation theory. Then there can be corrections And like any quantum theory, you can have perturbative corrections or even non-perturbative corrections. And they will go also with different powers of 1 over r. So in this case, 1 over r to the 18 is one of the dominants. Okay, so you can see that in most of the cases, so essentially in all the cases, you have the potential like sums of terms where 1 over r to the some power. And you have all of them combined, you can have a potential which is 1 over r to the 1 power minus 1 over r to another power plus 1 over r to the third power, and so then you have a potential, and then you want to find a minimum, as hopefully we'll get the sequence. So that is the picture. So these are the sources you can have from a string theory, where you can have sources of potentials, and the question is you turn all of them on and combine them or do calculations, see if that can give you a non-trivial minimum with the right properties as I explained before. Okay, so that is the rule of the game, essentially, what to do, and then you have to be more explicit and go in case by case and to compute exactly the values of this potential. But that is essentially the whole picture. You realize that all these powers I told you was 1 over r to some power. So at the end, those potentials, they all go to 0 when r goes to infinity. So that means when the radius goes to, so the size of the extra dimension goes to infinity, all the potential go to 0. That is natural because we have to recover the 10-dimensional solution as a solution. So that should be a particular case. That happens also not only for the size of the extra dimension, but also for the dilaton and so on. So essentially, the potential tends to look like this. We have what people call a runaway potential. So it goes always to 0 at infinity, and that was called. Was realized very early in the history of string theory in 1980s by Dine-Seiberg, and that is called the Dine-Seiberg problem. Why is it a problem? Is that because you say that at the end the potential has to go to 0 to infinity, and that means that any source of potential any source extra source that will give you a minimum will have that brings me back to the Dice-Saber problem. There is full control of your calculations only in the region 3. So, because that's when the coupling can be arbitrarily small. And so in region 2, the couplings can be small, but it can be 10 to the minus 2 or 10 to the minus 3. And that may be an expansion. That number may be okay, but may not be, is not under full control, because you cannot make the parameter always all the way to 0. So that's why it needs a lot of detailed calculations, and so that people are always debating. Okay. But model of that, there's a century-old, I call moduli problem, and that people, the question is, in the 20th century, why we do not see the extra dimensions? The answer is because they are too small to be seen. Now, the question is, why are they so small? In the 20th century, people say, well, we don't know. Now, in the 21st century, a combination of all these fluxes and quantum corrections and brains, that will give you a value that can say, well, we can find solutions where these are very small. So in that sense, this is, I consider that progress, in the sense that we can fix the value of the extra dimensions and find solutions where the extra dimensions we cannot see. And on top of that, you can get some cosmology and so on after that. So that gives us a picture of the multiverse that I will explore more tomorrow. That you can have many solutions because there are many fluxes, and so this interview that I told you give 10 to the hundreds or so solutions, and then that each solution is a different universe with a different cosmological constant, and you can go from one to the next. I will come back for this to explain this in more detail tomorrow. The nice thing about this is that since you have so many of these solutions, and there's 10 to the hundreds of the solution, 10 to the thousands, so the chance that you get one which is valued lambda 10 to the minus 120 is not 0, because there's so many. And then in that one you can leave, and the other ones you cannot leave because the universe expands so fast or recontracts. And that fits with the proposal of Weinberg in the 1980s about the anthropic prediction for the cosmological constant, 10 to the minus 120. In this sense, this scenario provides an implementation of that idea. And the important thing about Weinberg's prediction, he predicted it 10 years before or so. Claim. And so you need a big evidence. So that you have a big claim, you need big evidence. So you have to accumulate more and more evidence. So calculations have to be done more precisely. Other corrections that have not been computed should be computed, and this kind of things. So in that sense, I am on the side, of course, that this works. It's the generic case. And then, but there are some people who claim, oh, there may be that things that we don't know can go can go in the wrong direction, and there is no minimum at all. And then there is this conjecture that I think Wolfgang or Guri, other people came up, which is the de Sitter conjecture that said that there is no de Sitter solution in the string theory period. And that is what has stimulated this debate, because then I will make the claim for that also, that is a very strong claim with a very small argument, just doing some, essentially that's the basis is the runaway potential of the binary cyber. And the conjecture is true if you are in the domain, in the region of region 3 that I told you, the runaway. And it's obviously true. Everybody knew it. So in that sense, there's no. So but then and that is the only region where that's when you say you have full control, because that's the region where you can set the coefficient to zero, the couplets to zero, and so that will always be true, but it's irrelevant because it's the runaway behavior. Notice that runaway is different from quintessence. If people have mentioned quintessence, quintessence is runaway with a very flat potential, and that is very difficult to get. So it's as difficult to get quintessence as to get de Sitter. So in that sense, there is no progress. So just to finalize, I would say that it is still an open question, but I am on the side that it's essentially the genetic case is there, the calculations have been done, and you want to argue that there is no de Sitter. It is a very strong claim, I think. It's stronger than the other one. And then you have to come up with a strong evidence, and there's no strong evidence that there's no de Sitter. It's actually the opposite. So in that sense, I think that KKLT or variations of it, like LVS or so, are correct. But there are other questions that some people overlook, or most people overlook. Is that getting de Sitter is good, but getting de Sitter in a compactification where there is no standard model, it doesn't make sense, because at the end we want to explain the acceleration of the universe with the standard model. But if you don't have the standard model, you're just accelerating a universe without the matter that we want. So those are questions that I find more interesting, because then you have there are challenges to put all this KKLT or LVS or so within a format where you can also have the standard model, and then you can have the whole picture working. And that is something that people usually on both sides don't pay that much attention. And I think those are the questions that at the end will be the relevant for experiments. Sorry, I extended too much, but I'm a bit passionate about this.
Because of the time limit, maybe you think about. Forgot to mention Professor Quevedo was the former director of ICTP. And during his term as ICTP director, and with his permission, our institute, ICTP-AP, was founded. So let's thank Professor Quevedo again.
Thank you. Thank you very much.
Thank you much. Thank you much, Fernando.
Nice.
Thank you for a nice talk.
Thank you. See you tomorrow. Yeah. Bye-bye.
See you. Bye. So we take another few minute break, and we set up next talk. Okay.
So Professor Hurley is a world-leading expert on gravitation and in particular black hole physics. The title of his lectures are Geometric Origins of Linears in Flat Space. Let's welcome him. Okay, first I'd like to thank Yuanjun for this honor. And I'm from the Center for Joint Quantum Studies in Tianjin University. For those who are interested in a visit or even joining us, this is our website. And today I'm not going to talk about black holes, but the geometric origins of Yamuse in flat space. In string theories, the color fermions or Yamuse fields are not uncommon, as Professor Covedo already mentioned. Heterogeneous string theory has either E cross E8 or SO32 Yamuse fields. They do not have geometric origins. The Yamuse fields in areas during supergravities do have geometric origins at the sphere reductions, but the space-time they are living in the areas. Today's talk, I'm going to review these cases, but with the goal of finding the geometric origins of a certain Einstein-Yamuse theory in flat space-time. Since today this is a lecture, so I'm going to start with something pedagogical. Most of people here are quite young, and a wise man or woman would like to tell you, the more you learn, the less you know. This may be sincere and even true, but it sounds like a rich man bemoaning the pointlessness of being rich. This agnostic view of ourselves and our world overlooks the tremendous progress in our understanding of nature at the fundamental level. We, a creature size about 1 or 2 meters, hopefully in the vertical directions, master the physical laws governing the world of the scale of the size 10 to the minus 15 meters, the size of nuclear, to 10 to the 12 meters, the size of a solar system. We, a creature of less than 100 years lifespan, except for a very few we know who, understand how the universe evolves from 10 to the minus 11 seconds after its coming to being to the current stage of 13.7 billion years old. So picture this. All of the civilizations and cultures, different in environment and development, with different language and social conditions, dead or surviving, they all have one thing in common. They all observed the rise or set of the sun and the moon and the moving of celestial stars and planets. Mystic forces and legends were told to explain these motions, indicating there's an underlying desire for us to understand the reason behind. Newton's law explained it in a stunning mathematical precision. Such achievements are not an accident or guarantee. What is the underlying principle that allows fundamental physics to succeed? In my view, this success is related to the methodology. It is about 3 W questions asked by physics. One is what? It's about the basic constituents of matter. And the second is how. This is about their interactions. And third is why, the underlying symmetry principles. These appear to be rather simple questions everyone could ask, but that's not entirely true. For example, not every culture asks the question, what is light? Even though we all observe light. In fact, pursuing its answer propelled major developments in physics. How is in the Newtonian physics, this is a concept of force. The Newtonian physics, however, cannot explain why one of the the inverse square force law for the gravity nor for the electrostatic forces. In quantum field theory or Einstein general relativity, this non-local concept force is emergent from the local interactions. The question why is much more subtle and philosophical because you can always continue to ask, why, even the answer is given. What do we mean when we say we understand something? Quantum mechanics is far more accurate than the Newtonian mechanics. However, many claim they understand the latter, but not the former. So that's very strange because we typically distinguish a crackpot theory from a true science is that crackpot theory cannot give a precise quantitative descriptions. So from my point of view, underlying the symmetry may be the reason we can claim we understand why. So this is the focus of this lecture about symmetries. Symmetry is about beauty. Before Galileo, symmetry considered was typically discrete except for the continuous symmetry of a sphere. Kepler tried at first to use nested platonic solids to build a model for solar system with 6 planets known at the time. But he, of course, gave up this idea because he found that the orbits of planets are ellipse rather than sphere. Discrete symmetry may be able to explain some kinematics, but very difficult, if not impossible, to explain dynamics, since dynamics, as far as we know, is governed by differentiations. Galilei was the first scientist to realize the importance of continuous symmetry in physics. He hypothesized a universal principle of relativity, but he neither proposed nor limit to his principle to so-called Galilean transformation. Well, some symmetry is, so this leads to the next things. Not all symmetries are equal footing. There are what do we don't understand? You mean some symmetries are easier to understand than the other, right? If we, for example, if you have a platonic, platonic solids, if you have a cube, you have a 90-degree symmetries, those are not that difficult to understand. No, we have to assume we understand something. Well, right, that's fine. Right, let's go on. Well, in this case, here I'm not going to talk about quantum gravities, right? Anyway, right. So there are two important classes of continuous symmetry in fundamental physics. One is about coordinate transformation invariance or diffeomorphism. Another is about gauge symmetries. Here, basically, I assume that we understand what's a coordinate transformation. In symmetry related coordinate transformations are easier to understand. For example, time and space translation or space rotations, Galileo transformation. The reason why we understand them because we can all visualize. And in fact, our daily life is about the space-time coordinate transformation. You coming from here to this lecture, you get up in this morning, this is all about coordinate transformation. And I just assume this is something we do understand. So we have 3 types of space-time relativities. The easiest to understand, of course, the ordinary relativity that is related to the Galileo transformation. Another is the special relativity realized by the Lorentz transformation, which, if you go over the full Monty, give rise to the general relativity, which is a general coordinate transformation. Gauge symmetry, on the other hand, is more abstract. The reason why I say it's more abstract, if you think about the important thought experiments in physics, they are typically related to the coordinate transformations. I haven't heard of many or any thought experiment regarding the gauge transformations. So the next question is, what is gauge symmetry? We typically study Maxwell theory before quantum field theory. In the former, the gauge symmetry appears since we introduce the extra degree of freedom. Maybe that's what Jenkins talked about. In tensorial description of electromagnetic fields, where we have a field strength which is partial mu A mu minus partial mu A mu, or in the form language, F equal to dA. And this field strength is invariant under local transformations, where A mu is shifted by a total derivative. Of course, this way of introducing gauge symmetries does not explain why is it called gauge symmetry. What is the significance? Why is it sometimes called abelian symmetries? And why electromagnetic fields are related to the charged matter? So here I would like to talk about the origin of the gauge symmetry as a global symmetry of Dirac fermions. The Dirac equation is given by this, that is the equation describes the fermion-like electron, and it has a Lagrangian formalism given by this. And we can easily see that it is invariant under these phase transitions, where you have a constant alpha. Originally, of course, the Dirac equation was treated as a relativistic version of the Schrödinger equation. So the psi is treated as a wave equations. In this case, you don't have a Lagrangian, but you only have the equation here. In this case, it's invariant, can be invariant under the real constant scaling. This real constant scaling wouldn't work with this Lagrangian formalism, but it works equally well as the phase transition. This was initially introduced, and the reason why the symmetry is called gauge, the measure of scale. So this is really a misnomer, but later on, when we have a better understanding, we don't seem to have a better name for it. So it is still called the gauge symmetry. The symmetry is local, as alpha is a constant, independent on the coordinates, locations, x mu. So if we let this alpha to be local, to be any functions of any scalar function of the coordinates, then the invariance, the Lagrangian is no longer invariant, but the invariance can be restored if we introduce a connection, connection one form, where we can introduce the derivative to become to introduce this covariant derivative, where it's the ordinary derivative plus these connections. So that under this phase transition, but now it's a local phase transition, the connection transforms with this. This is what we have already seen, like the gauge transformation. Under this transformation, then the covariant derivative transforms covalently. Well, that's why I call it covariant derivative. It transforms in the same way as Dirac fermions. We therefore can promote the local symmetry, we can promote the global symmetry to local symmetry with a new Lagrangian, where ordinary derivative is replaced by the covariant derivative. And conventionally, we drop the local and understand that the gauge symmetry typically is a local symmetry. And this has astonishing consequence, because this introduces a connection. The introduction of the connection yields a cubic coupling to the free theory, where we have now have additional term which can be written as A mu, J mu, where this J mu can be viewed as source term, source current for this connection A mu. However, if we treat the A mu as a field, then the violation principle will force J mu equal to 0. This is because we don't have a connected term for the A mu. It is thus necessary to introduce a connected term to the connection. Respecting the gauge symmetry and following the two derivative linear dynamics, then the simplest Lagrangian is just the standard Maxwell theory. So this in a sense, is like the Bible, there be light. The total gauge invariance theory then is simply this term. It involves the linear series of electron and the max field together with their unique cubic interactions, from which then we find that the inverse square Coulomb's fourth law would emerge, and that is a standard discussion in the quantum field theory. Based on a rather simple deduction, suddenly the quantum electrodynamics pops out. And that is astonishing. And what is more mysterious is that nature follows it. So this is the reason, at least for me, why we would like to understand better the origin of this underlying symmetry. Although mathematically, of course, it's rather simple, but the nature simply follows this. And then why it follows these simple deductions. And furthermore, we discussed this is about Dirac fermions, which is a complex spinor field. We can also have the analogous discussion for complex scalar. We can promote a theory of a massively complex scalar with a global symmetry that is clearly have this form. And this can easily see why the Lagrangian is invariant as long as alpha is a constant. However, we can promote this alpha to be local so that we get a gauge invariance theory by introducing change this ordinary derivative to covariant derivative. And that theory then describes a photon, charge scalar, and their interactions. The complex scalar can be viewed in terms of two real scalars, that phi1, the real part, and phi2, the imaginary part. And then the starting Lagrangian is simply the two free massless massive scalars. And the original U1 transformation, which is e to the I phi, then can be viewed as SO2 transformations as phi1 and phi2, and that is something, of course, we're very familiar. This is just a rotation in our two-dimensional plane. For constant alpha, this obviously is above Lagrangian invariant. So the abelian symmetry then can easily generalize to the high-dimensional non-abelian rotational group. For example, this is just a rotation in the xy plane, but in classical mechanics, we have already learned that we can discuss rotations in three-dimensional space. And that is something we're going to discuss. We consider a system of three massive scalars of the same mass, and then it is given by this. Now, if you treat phi1, phi2, and phi3 as x, y, z as the coordinates, then this is really effective Lagrangian of the three-dimensional simple harmonics with the same spring constant. And of course, in this case, the force of this spring constant is a central force. We have a rotational symmetry. So similarly, in this field theory with three massive scalars, then it's invariant and the constant orthogonal transformations given by this. And for infinitesimal transformations, then Mij is just delta Ij plus epsilon Ij k alpha k, where in this case, now this alpha is an infinitesimal quantity. Then the scalar will change. So this is really the same thing we discussed in the classical mechanics, but in the guise of quantum field theory. So we use the notations like the cross product, like vectors here. If the transformation parameter alpha is local, then we need analogously introduce a connection, a mu that is also like a vector here in this phase space. Well, in this space, it's not an actual space, but the space of the three scalars, and so as the phi transforms like this, then this delta, the A mu fields transform this. Then the corresponding covariant derivatives acts on scalar will be given by this.
So you are gauging the global symmetry.
Yeah, that's indeed, that's exactly what we did in the earlier case at the U1 or SO2, right? We start with global symmetries. Then you gauge it by setting the parameter to be local. Then you find Lagrange is no longer invariant. You have to introduce connections. So here you just generalize this idea that this symmetry group is no longer U1 or SO2, which is abelian. Now it's a general SO3. I choose SO3 because this is what we learn in classical mechanics about rotational groups. And we can do the exact same thing, basically, right? And the group is SO3, so we have to introduce three gauge fields, three connections, which in this case just happens to form a vector representation of SO3. That's why we have this vector notation here. But it has the vector, forget about this space-time coordinate indices, but this has an IJK indices here. Right. And the three components of this A mu vector, which is I, are then the non-abelian Yamus of SO3, and the invariant field strength then takes a form. So if this group is abelian, then we don't have, this term will be articularly zero. We would get what we had before. Now we have some additional structures, A mu plus A nu. And it transforms as an SL3 vector given by this. So they transform the same way as how the scalar transform. The scalar form a vector representation as SO3, and the field strengths also transform in that same way if you look at this transformation versus this, basically. So then the four invariant Lagrange then is given by this. And the last term basically described by pure Yamu theory of SO3, which is isomorphic to SU2. So this, of course, is a special case of SO3. It's easy to visualize, but the generalization to general Lie group is quite straightforward, which I'm going to do. Again, mysteriously, the nature obeys such a mathematical construct. For example, the SU3 QCD, where the matter fields are the SU3 quark fermions instead of the scalars described here. So we can see that compare the diffeomorphism or general coordinates invariance versus the gauge symmetry. Then gauge symmetry is mathematically more elegant since the transformation is linear. It's just simple linear transformations. General coordinate transformation is nonlinear, so it's much more messy. But the diffeomorphism is easier to understand since we can visualize them. We cannot visualize scalar or spinor fields easily. In fact, we don't even see what the electron is, so let alone visualize the Dirac fermions that describe it. And hence difficult to understand the origin of its intrinsic symmetry. Geometricalization of this intrinsic symmetry of field is thus a way of helping us to understand their origins. And this is the focus of this lecture. So this is a kind of pedagogical introduction to my main talk. So if there's any questions, of course, what I'm talking about is really kind of probably appears in any quantum field theory textbook, right?
Why do you call Yamies the gauge symmetry Yamies is linear?
The transformation law is linear.
The field strength is linear, but
no, the field strength is not linear. You have a kind of this kind of you have a linear term plus non-linear term, but the important is that the transformation is linear.
The transformation of a field strength is linear.
Yes.
The transformation of the gauge field itself is not linear.
Well, okay, it depends on how you view. In some sense, you know, typically some people would call this a non-linear part, but nevertheless, you don't have a quadratic kind of this, right? So it's much more kind of well organized. Okay, I made a mistake. I should not. Yeah, okay, yeah. Anyway, you can see that the transformation law is much more well organized than the general coordinate transformation. Okay, right. But nobody going to say that Einstein's theory is not a linear theory. So I just finished the introduction of Yang-Mills fields. Then I'm going to talk about the geometric origins of abelian gauge symmetry, and then the geometric origins of Yang-Mills fields in curved spacetime such as ADS or de Sitter spacetime. And finally, I'm going to discuss the geometric origins of Yang-Mills in flat spacetime. So the geometric origin of abelian gauge symmetry is by this Kreutzer-Klein approach. And this is based on the Chris Pope's lecture notes on Kreutzer-Klein theory. In the early days of general relativity, only two fundamental forces were known, gravity and electromagnetism. It is thus natural to unite them in five-dimensional pure gravity. That was that is what is a Kreutzer-Klein theory is. It's natural because gravity is a two-index tensor theory, while Maxwell is a one-index tensor or vector theory. So you consider a five-dimensional theory which has an indices m, which can decompose into mu and z. Then the GMN can have the lower dimensional metric. In addition to the off-diagonal term would have like a mu. So we appear to have a theory that have both g mu mu and a mu. But wouldn't the theory behave like, would the theory behave like d equal 4 rather than d equal 5? We cannot just, for example, we can do the same decomposition of a four-dimensional space-time, but no matter how you decompose this word is still four-dimensional. The problem can be solved by considering five-dimensional space-time as a four-dimensional one together with a circle. In a flat space-time, then we consider Minkowski 4 plus this S1, which has a coordinate z, and this z describes a circle of L. Physical field then just simply follow the Fourier expansion given by this. Then the massless scalar in 5 dimensions then would satisfy the 4-dimensional box plus some collections, and this collection is related to this the n modes of this Fourier expansion. So when n equal to 0, that we call the 0 mode, then we simply get the massless fields in 4 dimensions. And then in addition to this massless mode, there's an infinite tower of massive Kreutzer-Klein modes. So if L is something small, as Professor Covido mentioned, but we didn't, at least I didn't know why, but he knows, relate to the modular stabilization. But here I'm not going to pretend I know why L is small, but just say this is just a phenomenological requirement. Then the massive modes can be ignored in the low energy physics, effective physics. The scalar phi then behaves like a 4-dimensional 0 modes where the subscript is typically dropped. So this is, in fact, the original NZ. where you split the metric into the 4-dimensional one plus internal one with a twist that's related to the Kruskalin modes. And in other words, we keep in only the 0 mode, then you have the the lower dimensional metric, then you have a Maxwell field, and then the GZZ is assumed to be equal to 1. And it turns out that the Einstein equation in 5 dimensions, if we look at this equation, then restricting to mu directions, and if you do a calculation, and that is exactly what you get. And this is precisely the 4-dimensional Einstein equation of Einstein's theory coupled to a Maxwell theory. Furthermore, substituting the nz's into the Lagrangian, we will find this is a Lagrangian, and the equation motion of this Lagrangian, the Einstein equation precisely produces. This seems to be worked fairly well. However, there is an issue about consistent issue. The above discussion was too simplistic. A careful examination. Here I'm writing everything in the view band base. If you look at this curvatures in the high dimensional curvature, and these are the 3 terms, the AB and AZ bar and ZZ bar. These are the view band base. That's what we have. So this appears to give us desired lower dimensions because this term equal to 0. And if you look at the G hat AB, and that's exactly what we have. However, that's not the only equations we have in 5 dimensions. The full 5-dimensional Einstein equation, where the Einstein tensor vanishes, requires the whole metric is Ricci flat. That means every term has to be 0. If you look at every term have to be equal to 0, then you find you would have force F squared equal to 0, and IAB equal to this, IAB equal to this, not consistent with these equations. So not all the equations are satisfied by lower dimensional Einstein-Maxwell theory. The problem was caused by nz's GZZ equal to 1, which is too restrictive, since GZZ is a scalar mode from the view of 4 dimensions, which should satisfy its own equation of motion. So the proper thing to do is that you need to write GZZ as a scalar field. And this is a kind of typical way of writing the 4 Kruskalin nz's. And if we write them in this view band base, and the consistency basically requires that beta cannot be 0. The alpha is not that important because this is just a conformal transformations. It depends on which kind of lower dimension Lagrangian you want to have. So if we want to if we treating first to calculation, treating phi as a constant, then the Einstein-Hilbert action in 5 dimensions turns out to be this. So if we want to write the 4-dimensional, a lower dimensional metric in the Einstein frame such that it does not have a scalar couplings, then we will say beta equals minus d minus 2r. Then let's assume alpha now is no longer constant, and then you find it has a connected term given by this. And typically we would want this connected term convention that this connected term has a parameters 1/2. So this would fix this alpha parameter. Then this is just a matter of calculations. You look at all the curvature tensors in various spaces, then you find now we require every term has to be equal to 0. And because the 5-dimensional metric is Ricci flat, then this equation motion of a lower dimensional field can be derived from this Lagrangian, and this will be equivalent if you substitute this whole nz's into the 5-dimensional Lagrangian. You would also get these Lagrangians. So we thus obtain the consistent Kruskalin reduction on the circle. So here basically is a repetition of the Krutz-Klein ansatz. So we have from D+1 to D-dimensional field, where the scalar is parameterized with these two alpha beta. Then the D+1 dimensional gravity turn into an Einstein-Maxwell dilaton type theory with a specific couplings. For example, in 4-dimension Krutz-Klein theory, then the coupling is minus square root 3. And in 3-dimension, this become minus 2, 5. And then of course, in 3 dimensions, a 2 form is codue to an axiom, and this become a standard kind of a complex scalars. The KK theory has a U1 gauge symmetries generated by this vector because the Lagrangian is given by its field strength, and the field strength clearly is invariant under this gauge transformation. So what this gauge transformation does from the D+1 dimensional point of view, this symmetry is simply a coordinate transformation because the Lagrangian basically is given by, this metric is given by this. So now, if this Z goes to Z minus lambda, plus then A goes to A plus D lambda, then this term precisely invariant. So we can now see that the origin of this gauge symmetry is simply the diffeomorphism, the residual diffeomorphism of these ansatz. Now let's look at how other fields other than the zero mode. Under this transformation, the metric and the Krutz-Klein phi are singlets. Those fields are singlet under this gauge transformation. They are not charged. However, if you look at the massive Krutz-Klein mode, if Z goes to Z minus lambda, then you find the corresponding, the lower dimension, the massive modes now pick up this phase effect. So we can now see that the zero modes are neutral or singlets under the U1, and the massive modes are charged. The consistency of Krutz-Klein reduction, if we have a group action like U1, it is always consistent to keep all the singlets while setting all the non-singlets to 0, because the singlet cannot contribute solely to the source of a non-singlet equation motion. So the reason why the initial Krutz-Klein approach was failed because they didn't include all the singlets. They messed up the singlets of the scalar. And once you keep the scalar in, then you have, under this ansatz, you have all the singlets under the these U1 symmetries. Then the reduction is guaranteed to be consistent. So we find that a special Einstein-Maxwell dilaton theory can be obtained from pure gravity, but it's not Einstein-Maxwell theory. The massless dilaton scalar cannot be decoupled from the equation of motion. So this is unfortunate because it does not exist in our universe. So this theory is incorrect. So then one can ask questions, what about a high-dimensional pure gravity? It turns out that we cannot consistently embed Einstein-Maxwell in pure gravity in any high dimensions. That is just a no-go theory. The massless scalar modes cannot be all decoupled, no matter what you do. Embedding Einstein-Maxwell theory in M theory or string is possible and known, but this theory involves high-form gauge symmetries, like M theory have a gauge symmetry associated with the 3-form antisymmetric tensor. So maybe you can explain the gauge symmetries from M theory, but it involves a high-form gauge symmetry. So it will be like using the arcane and difficult words to explain the simpler words. So this is not satisfactory either. So a pure geometric origin of U1 gauge theory of electromagnetic Einstein Max theory does not appear to exist. So this is a bit of failure. Nevertheless, although we cannot embed Einstein Max theory in pure gravity, but Krutz-Klein theory, like EMD, does have a pure geometric origins. And the gauge symmetry of the Krutz-Klein vector A mu does have this origin of gauging the U1 isometry of the S1 associated with the coordinate Z and the corresponding Killing vector K equal partial Z. This can be generalized to N torus, where the Killing vectors given by Z, which are commuting, generating this U1 to the N group, and the reduction NZ, if we only look at the Krutz-Klein vector, is given by this. And this leads to the N number of the Maxwell field. Now, what about Young Muse? If the internal space is not torus, but a round sphere, its isometry group then is SO n plus 1. We can apply the Krutz-Klein idea on Sn. We will get n plus 1 over 2 number of one-form fields carrying the isometry group index SO n plus 1. And so these fields form a kind of antisymmetric tensor representation of this SO n plus 1. And this was first considered by Pauli before the concept of Young-Muse fields. He thought about this in 1953. And Pauli imagined a 6-dimensional space-time because 5 dimensions already been considered by the Krutz-Klein. So he imagined a 6-dimensional space-time as a product of 4-dimensional Minkowski and S2. Then he wanted to get certain, at that time it wasn't even called Young-Muse yet, something coming from S2 as the isometry group of the two-sphere, which of course is SO3. But this idea did not work for obvious reasons, that Minkowski 4 cross S2 is not a vacuum solution of Einstein gravity in 6 dimensions. And the problem can be resolved, even though the problem can be resolved by adding a cosmology constant so that the vacuum becomes ADS4 cross S2. However, the reduction is not consistent, unlike the Krutz-Klein torus reduction. And this probably is the reason why he gets angry when C.N. Young proposed Young-Muse theory. So, because he did thought about that. So why there is an inconsistency of the sphere reduction? If we consider Einstein gravity with a cosmology constant given by this, then we consider reduction NZ with all scalars turned off for now. Then it's given by this. So this is the internal directions. If the AI is set to 0, then this is just a certain sphere. So we assume there is a lower dimensional space, either Minkowski or ADS, cross certain spheres. The Einstein equation restricted to these directions is given by this. Now we know in the earlier, for the torus, this Killing vector just simply commute and they are diagonals, and this just given by delta ij. And we know that this stage, this works. It doesn't work if we don't add scalars. But if you consider sphere, this equation doesn't work either because the Killing vector of the sphere and this contraction depends on the internal sphere coordinates, this ym. So on the left-hand side, this equation, the lower dimension equation, clearly is independent on the internal direction y. While here, this part is independent on the y coordinates, but this one depends on. So this equation cannot work unless either this equal to 0 or both these two terms equal to 0. So this was observed in 1985 by Mike Duff and Chris Pope. However, they also observed some miraculous thing happens in 11-dimensional supergravity, which was constructed by Kramer and Julian Shirk in 1976. And the Lagrangian, the bosonic sector of Lagrangian is given by this. And we all know that this theory has ADS4 cross S7 or ADS7 cross S4 vacuum without needing a cross-Maury constant. And if we now focus on these Einstein equations that didn't work previously, then this energy momentum tensor would contribute an additional terms. And here this piece contributes this, and group them together, then one would find this, the coefficient now becomes this, which for the spheres simply have this identity delta ij. So now this leads to the Einstein equation work. Of course, we know this working of this is not good enough. We also have to consider all the scalars, but this is the first step. And this problem was later solved by DeWitt and Nicolai a couple of years later, but they didn't provide the ansatz for the four forms, which was later done by Nastasi et al. So let me repeat, this early discussion does not mean that the sphere reductions of 11 dimensions must be consistent, since we only look at the Einstein equations in the mu-nu directions. We did not look at the other direction in the Einstein equations. We did not look at the equation for also the A3 field. So as we saw earlier, that even the simplest S1 Krutkin reduction showed us that scalars are indispensable. It took quite a long time to figure all this out, but the upshot that the reduction is consistent. And one would get this four-dimensional gauged SO8 Young supergravity in 4 dimensions as a consistent 7-sphere reductions of 11-dimensional supergravity. In particular, if we, in retrospect, then this Lagrangian of the 11-dimensional supergravity, this term, of course, is a pure setting a scale, so I can choose to be 1/2. Then you find this 1/6 is a non-trivial parameter that you cannot change that if the first two terms are fixed, the coefficient. And this 1/6 is a non-trivial parameter that plays an important role in various things of supergravities. That this 1/6 is required by supersymmetry. If you don't have this 1/6, then you don't have a supersymmetry. And 1/6 also implies the existence of this U-duality group called En plus N, U-duality group of this M series. And then we find that 1/6 is needed for consistent sphere reduction, even though it is not required by the two ADS cross sphere vacuum. We mentioned that here, this theory has ADS4 cross S7 and ADS7 cross S4. This vacuum is independent of this last term. Okay, so then it's natural to ask these questions that how to tell if a sphere reduction is consistent or not. In general, that pure gravity that Mike Duff and Pope demonstrate that it will not be consistent. But we have a special cases of 11-dimensional supergravity. You can have a sphere reductions in a certain sphere, like 7-sphere or 4-sphere. So it is a natural to ask these questions. Okay, the consistency also requires some kind of very special properties of this theory. Then it is natural to tell that how do we see if a theory is consistent to have a sphere reduction or not. So I think this is about 15 minutes, right? Yeah, I think I control my time very precisely. Okay, I'll stop here, right?
Okay. Thank Professor Liu for the very interesting talk. Any questions?
Why should we care about theory?
Because this is my original motivation. I want to have a geometric.
Because Professor Liu said Wolfgang Pauli tried. That's the way.
I want to have a geometric interpretations of the gauge symmetries. Now, for anyone who say that I understand gauge symmetry easy. Yes. Now, if anyone say gauge symmetry is so easy to understand, I don't need any, then that's fine. The torus compactification, then it won't work, right? But this already we see an example here. 11-dimensional supergravity do not have gauge, non-abelian gauge symmetries. However, the 4-dimensional gauge supergravity do have SO8 gauge symmetries. Yeah. So if I just give me this SO8 gauge symmetries, then okay, what does it mean? So my introduction basically, it's very difficult to understand the fundamental reason of gauge symmetry. Of course, the mathematics is very easy to understand. Now we can see this gauge symmetry of SO8 literally coming from purely from 11-dimensional super through geometric isometric.
Even doing fourth dimension, lower dimension, can still group somehow together.
You don't have a non-abelian.
We can get some, for example, the enhancement of this kind of for specific body of the contact radius.
If I don't think you can do that unless you have a kind of string origins.
Yeah.
Yeah, but that's the whole point. For you, maybe it's very easy to understand what a string or the string origin is. To me, to use string theory to explain something
in that sense,
is like use arcane word to explain something simpler. I find gauge symmetry, compared to string theory and gauge symmetry, I would say string theory is easier to understand. Sorry, I would say gauge symmetry is easier to understand. If you use string theory, for example, string theory competing on some singular points of the modular on the internal space, you would get a gauge symmetry enhancement. But to me, this is a mysterious thing. This is not a geometric origin. Geometric origin is the isometric group of the space-time. That is something I understand because it's just a coordinate transformation. So I split the symmetry in two parts. Those I can understand called the coordinate transformation. This I don't understand. One of them is gauge symmetries, right?
I want to make clear that is the reduction always consistent when you include the dilaton?
Well, it depends. If you consider torus reductions, then it is always consistent because it's.
I mean, when you make the ansatz, you drop the dilaton sometimes.
If a case of the torus, for example, then you have to include in most cases you have to include the dilaton fields because all I can tell you is that if you include all the singlets under certain symmetry transformation, then it's guaranteed to consistent. But sometimes even if you drop some dilaton, it's still consistent. But that requires some kind of miracle, kind of specific equations.
So this is a very special case. I think
this one, which is a very special.
There is no dilaton in.
No. Okay. This case we don't have a dilaton, right?
Okay.
But the point is that even without this equation, basically will be independent on the dilatons.
So what's the?
So even if this works, we still need to look at the dilaton equation.
What's the intuitions whether you should include
You always need to include the dilettantes. But let me look at the cases where the dilettante is said to be constant or something like that.
Okay. Yeah.
Right. Then I want to look at whether the equation is already working or not. For those equations working, then I still look at the equations on dilettantes. Right.
Because time limit, maybe we can postpone more discussions to private conversation and to the dinner. Okay, let's thank Professor Liu again. Okay, we still need another few minutes to set up the next lecture.
Could you speak? Yes, right. Oh, I see.
Oh, can you hear me?
Yes, we can hear you. Hi.
Okay, great. Can you also see the screen?
Francesco.
Hi, good to see you. Hi.
Good to see you. We just take a few minute break.
Yeah, sure, no problem.
Okay.
I try to anticipate a little bit. So can you see also the screen?
Yes, we can see your screen.
Okay, wonderful. Let's see if it works.
Yeah, everything is
It works.
perfect.
Perfect.
Okay.
Excellent.
Okay.
Okay. Wonderful. So then I'll be just waiting.
In starting 3 minutes, maybe.
Right, perfect. No problem.
Okay.
Talk to you soon. I'll just mute myself so that.
Okay, Francesco, are you ready? We probably can start your lecture.
Yes. All right. Can everybody hear me?
Yes, we can hear you. So we're going to start the third lecture of this afternoon session. So the lecturer is Professor Francesco Sannino from Southern Denmark University. He's a director of a Quantum Field Theory Center at Southern Denmark University. Professor Sannino, he is a leading expert in quantum field theory and particle physics. And recently, he's very interested in black hole physics. So the title of his lecture is Universal Description of Quantum Black Holes. Let's welcome him.
Thank you. Thank you for having the patience to listen to me. By now, you'll be a little bit tired, but I hope that you will enjoy. So please me stop anytime if you have questions. I'm pretty excited about this subject. I'm recently diving into it myself, and I think there is a lot of interesting things still to explore together. The first part of the lecture is supposed to be very flat in the learning curve, so it should be something that will probably make you relax a little bit and enjoy. And the second part is a little bit more involved mathematically, but hopefully the blending of these two will be such that you can, have a good understanding of what's happening. Now, why did I get interested into this? Well, I mean, I heard about gravity many times. I remember when I was a graduate student at your age, I talked to my advisor at the time and asked, where should we work on gravity? And that was about 40 years ago. No, 40, sorry, but 25 years ago. And the answer was, I think it's not much going on in gravity right now. I think it's better if you do more particle physics. Now, there's more going in gravity right now. I would say there is mostly still classical gravity in practice has been tested, and very little is independent way to understanding quantum gravity. Approach quantum understanding of quantum gravity, in particular quantum black holes, using particle physics methodologies, in particular effective ones. So that is actually more or less what you're going to hear. And I will see that it's going to be successful, at least at the very, what we're doing so far. It's pretty nice and exciting. But first of all, I mean, what I'm going to say, and in case you missed anything, you already get it from the first slide. So even if you don't are unable to follow through everything, I'm going to describe is an effective metric description of black hole metrics. I will give you the general expression of the Hawking temperature corrected that whatever theory of quantum gravity you're going to use, you will have to respect, provided it provides the metrics. We will also see that we're able to derive universal constraints for generic models of quantum gravity. We will even be able to rule out models of quantum gravity put out in the literature or model of quantum black holes because effectively they don't respect these constraints. And if you're interested in the phenomenology of black holes, this will lead to a relevant parameterization of black holes that does not depend on the specific model. Okay. It's a consistent bottom-up approach for quantum gravity. Is it clear? So I'm trying to see if I can see people nodding in the audience. I can see some of you. Is it that clear enough as a message? Is enough you nod, huh?
Here. So we're going to... It's clear. We're going to stop you, interrupt you whenever we have questions.
Okay, wonderful. So now, why we're interested in black hole? First of all, because we can hear that, right? In fact, we've been able to award the Nobel Prize in Physics in 2017 when we saw we were able to hear actually the gravitation bang coming from two black holes colliding. This happened on September 14, 2015, and the gravitational waves were observed for the very first time. There is nothing new in terms of theory. It was already predicted about 100 years ago. And indeed, it comes from the collision of two black holes. It took about 1.3 billion years for these gravitational waves to arrive to the LIGO detector. And three gentlemen received a Nobel Prize in 2017 for the theoretical and the experimental observation of these gravitational waves. Effectively, LIGO is an immense, huge interferometer. Okay, so there's actually two legs, each of them of 4 kilometers. And when the gravitational waves arrive on Earth, they are going to squeeze in the two directions these arms. And at this point, you can see the small fluctuations. Now, what we can say that effectively humans have been built the most precise ruler ever. Right, I mean, because it can measure a fraction of a proton in length, which is insane. If you just think about it, sounds like much more fancy than Harry Potter, right? In terms of physics, you can actually measure something that is only a fraction of a proton. Fermi. Not only we can hear them, we can also see them. Very recently, we've been able to peer into the abyss thanks to the Event Horizon Telescope, which is an array of telescopes that have been synchronized. So these are synchronized, powerful radio telescopes have been combined observation from multiple of them. And the original observation of the first black hole involved basically 6 observatories, Mexico, in Mexico, Hawaii, Arizona, Chile, and Spain. And the targets, what they were actually looking at, were supermassive black holes. Okay. Now, how much data they needed to have to be able to pin down the image of a black hole? I mean, I love this way to remember it is that you need about 5 petabytes of data, and will correspond to a selfie collection of over a lifetime of 40,000 people. Okay, so you can either have 40,000 people over each of them, their lifetimes stored in Facebook or any other social media, or you can actually get some amount of data that will be enough for pin down the image of a black hole. This is an immense success for humanity. And this is a beautiful picture of the sub-millimeter array, ALMA, which is Atacama Large Millimeter Array, which is part of the Event Horizon Telescope network. I think this is really amazing. And that's what you see. Now, I mean, to an untrained eye, this very much looks like the bottom of a coffee stain, right? So when a coffee actually, you put your coffee mug on the table, that's what you see effectively on the table. Now, this is the first ever image of a black hole. It is M87 and is 55 million light years from Earth and about 6 billion the sun masses. It is insanely huge, right? But how do we know it's actually a black hole? It's not just, for example, a reconstruction fake. Well, because you can observe it at least twice. And this was first done in 2017, April 11, and then 2018, and you see it again. And you see that the ring has moved, right? The ring has moved by about 30 degrees. And that actually movement is consistent with the expectation of the photon ring to actually move around the horizon. Okay, you don't really see the horizon. You see something which is about 3 radii from the actual spatial horizon. So the black hole is actually inside this region. Okay. In space, on the left, you see the actual black hole, right? What we see is the image of a black hole, which is distorted by gravity. On the left-hand side, it is the graphical representation of how this overall would actually be in space. On the very bottom to the right, you can see my cursor, right? So this is the event horizon, which is about 1/3 of the distance from the photon ring. That's what we actually see. And this is the simulated image. So what the Event Horizon Telescope do, they simulate the potential image and then they confront with the data. It's an immense kind of machine learning or artificial intelligence way to reconstruct the image of a black hole, okay, from all the petabytes of data they have. It's remarkable. And the Nobel Prize actually then went to, I think this was probably to amend for some of the oversight that happened before, to actual a theorist and two experimental colleagues. And these are Roger Penrose for the discovery that the black hole formation is a robust prediction of general relativity. Now, it is not by chance that Penrose could write this paper in 1965, because Einstein had died the year before, and Einstein was vehemently opposed to the idea of black holes, even though he supported originally. It's a beautiful story. Even though he supported immensely at the beginning Schwarzschild, when he came up with a solution, he did not recognize at the beginning that there could have been a black hole, as since the idea of black holes started actually becoming more and more relevant, Einstein never really accepted that. So it was only from 1965 on that the small community of black hole believers at the time could actually flourish. So it's kind of remarkable indeed that the paper by Penrose actually appeared in 1965. So what he actually showed that not only black hole can exist, but they can actually form in a stellar collapse, okay? And that's why he actually got the Nobel Prize in 2020. Now, we had already seen black holes. I mean, by seeing, we already felt black holes. And this reason why Rainer Genzel and Andrea Ghez got the Nobel Prize the same years. And they saw it, actually they saw our own black hole, which is a Sagittarius A star. How do you see a black hole if you can't, hear it, or you cannot make an image of it? What you can do, I'll get back to it in a second, is actually to look at the motion of stars around the black hole, okay? And this is pretty fun. Let me go back to Penrose, okay? So if you go back to Penrose, there is a very simple way to understand what happens. And I love this picture. So if you look at what happened, you see that matter will at one point fall into the singularity. So the gravitation GR in the black hole forces matter toward the singularity. Now, in the case of Schwarzschild, we have a singularity at the classical level. This means, for example, the richest scalar basically becomes infinite. But the point is that as soon as you cross the horizon, what before was space now becomes time. So what I can say is that as soon as you cross the horizon, it's only a matter of time before you reach a singularity. And this is actually a beautiful way to actually understand this. That is why in the black hole space and time switch roles at the horizon. At the singularity, the matter density is infinite, and time ends. Now, whether this is true at the quantum level remains to be seen, okay? If you have a three-dimensional black hole called a Bittizer black hole, there is no singularity at the origin, okay? Now, on the right-hand side, you see how an observer from outside will actually see what happens from an observer that is observing matter falling in. Matter will never cross the horizon. It would be basically all be around the horizon. Okay. Now, back to the observations. Now look at the Milky Way. The Milky Way, this is an insanely super simplified description of the Milky Way. We have Sagittarius A star. We, you, me, sit at about 26,000 light years from the Sagittarius A star, which is the region of space. I'm not saying it's a black hole at the moment. It's just a region of space at the center of our galaxy. Our galaxy is shaped like a flat disk. It is about 100,000 light years across, and it's a spiral made by gas, dust, a few 100 billion stars, for which one of these is our sun. Our sun, if you were to put it on a map and kind of grade it with respect to the other star, is actually a pretty mediocre star. Okay, so it's actually not the brightest, it's not the biggest, it's something extremely mediocre as a star. Nevertheless, it supports life, so we should be very thankful for that. And we are, as I said, about 26,000 light years away from the center of our galaxy. So how do we actually analyze the center of our galaxy? Well, what you can do is look at the orbit of stars around the center. In particular, you can look at S2. And our colleagues have been observing that star for 17 years. And there is a movie that I'm not showing it to you that I actually very much will suggest you to have a look at, which is the compressed 17 years motion of the star around this little tiny point here. This tiny point here is smaller than our solar system. So this is insanely tiny. And what happens is that as the star goes around, it goes a blip, and then it goes up, and then it's blip and goes up. The blip here is very rapid, okay? So and using the American expression that it works like a black hole, it looks like a black hole, it is a black hole. And that is actually why we believe that Sagittarius A star is indeed a black hole. It weighs about 4 million solar masses. This can be measured from the orbit of the stars around it, and it's smaller than our solar system. So we kind of feel and kind of believe that indeed that is a black hole. Make sense? So basically, this is the reason why we, our own even colleagues, and then working on the Event Horizon Telescope, could actually peer into this region of space and try to see whether they can actually see it. So we can say that this is a theoretical physics triumph, right? If all of this is consistent with classical gravity. That's amazing. You know, it was 1925, general relativity, around that, 2015, so around that year. So in 65, Penrose suggests indeed that black hole can form, astrophysical black hole can form. So what next? What can we do? Let me go back to classical gravity. So it bends space and time. This is the famous Einstein equation, right? Equation of motion. On the left-hand side, you have the metric. On the right-hand side, you have matter. Now, there are two quantities here highlighted in blue and in red. One is what's known as a cosmological constant that you, as you know very well, Einstein wasn't sure about it, so he first put it in, then he put it out. But effectively something you can add in the Einstein equations. There's nothing forbidding it. And then you can, of course, have matter like you and me, and then matter goes to the right-hand side. I mean, this division to put to the right or to the left, this is arbitrary. You can always put to the left of the equations. There is absolutely nothing that forbids you to do that. Now, this equation is technically an equation of elasticity. And that's why we can say the space and time warps. And without any doubt, shows that to this extent of the description of gravity, gravity is a geometric force. But now, if you take the same equations and you consider the non-relativistic limit, this equation describes basically, as I said, elasticity. So if you sit on your chair right now, if you want to describe your chair, rather than going at the atomic level, but just as an effective description, you're going to write a similar equation for how the chair behaves under stress. But surely you would not be saying that this is a fundamental description of the chair, right? Make sense? You'll be saying, okay, I know it's made of atoms, So I'm pretty sure that there's something more fundamental about that. So it is a profound but not fundamental description of space-time. I'm sure you read the entire book by Thorne, right? This huge black book, right? Everybody should read it completely, right? If you don't have the patience or the energies to read it completely, I think I will suggest to read at least the last chapter. So I read the last chapter of the book because I think I probably knew I would never be able to go through the entire book. And if you read the last chapter, it's about indeed this observation I just made. Sakharov wrote, I mean, the Einstein equations for gravity are the equation for elasticity. And you will never think that the equation for a table is actually a fundamental description of the table. It is a very effective one. It works really well. And I love that comparison. So I truly believe that the Einstein general relativity is indeed a beautiful description of space-time, but at a very effective level. At a more profound level, there can be different possibilities. You heard before string theory, there can be, dynamic triangulation, there can be asymptotic safety in gravity, there can be tons of other theories, but clearly we have to have a more profound understanding of space-time. We might also kind of resolve the Schwarzschild singularity at the origin of the coordinates. So, but how do we move forward? I mean, you heard about gravity, either classical or quantum, many times, even in courses or even this meeting. But how do we actually like to parameterize our, if you want, ignorance about gravity? Well, one thing we do know is that on quantum gravity, it's adults with quantum field theory. Now, quantum field theory was born to reconcile quantum mechanics and special relativity. If once you apply quantum mechanics to special relativity, you find out that it violates causality. So in the 1920s, 1930s, 40s, and 50s, a theory of quantum fields was developed indeed to compensate for the backslash of quantum mechanics and special relativity. It seemed clearly that Einstein was playing tricks with quantum all the time, right? First, special relativity was adults with quantum mechanics, so you went quantum field theory. But then Einstein comes back later with general relativity, and now if you try to quantize general relativity, you find out that this theory is not well defined when it comes to the quantum corrections, right? It's a theory which is non-renormalizable. So on the right-hand side, you have basically a little simple-minded picture of saying that you have particle physics at the bottom of here and some quantum gravity. So one of the current way to go forward is to say, I don't know what quantum gravity is, but let me just postulate a sufficient number of constraints that tells me that only a certain type of particle physics can be mapped into a fully consistent quantum gravity theory. Many of these ideas come from string theory, and the particle physics that doesn't enter into what people would call the dry land is actually in the swamp land, so you have to throw them away. For example, you have principle like you expect that global charges are destroyed by quantum gravity. And that means that your particle physics can only have gauge symmetries, but not global symmetries. Okay? So, and so forth, so on. But many of these are only, speculations on what quantum gravity really has to be. Right? Nobody could just say this is a theorem. In principle, we should not even, it's not even clear we have a Lagrange description of the theory. I'm recently working with mathematicians, for example, for population dynamics, and they say, well, why do we need a Lagrangian? As long as we have actually the dynamical equation of motions, or what they call PDEs, partial differential equations, you don't really the Lagrangian, Francesco. I think this is an old-fashioned way to think. We don't really need Lagrangian to do that. So in principle, we don't even need Lagrangians to describe nature. It's just something that physicists love very much to write. But we do believe that a more primordial concept are symmetries. And symmetries do shape quantum gravity corrections, okay? So I do believe that symmetries do play a more foundational role in our understanding of nature, much more than Lagrangians do. So you can invoke a top-down approach. So you're generally smart, and you come with your favorite theory of quantum gravity. Now, I'm pretty sure that I'm missing some of the quantum gravity theories, right? But this is really, how do you say, a laundry list of potential quantum gravity theories. You can have superstring theory. You can just take the ordinary Einstein-Hilbert theory, try to quantize it. You know you're doomed because of the third order imperturbation theory, fourth order. Things will break down. You could have F of R gravity, which means that just you take a specific sector of potentially gravity theory, the ones which consider only the Ricci scalar and not. You can stop at R-squared gravity because R-squared gravity is normalizable, but it has many other issues like unitarity. Then, you can start becoming fancier and fancier. You can have higher spin gravity, loop quantum gravity, tensor networks, spin foams, dynamical triangulation, asymptotic safety in gravity. And, eventually, as long as they have the Newtonian limit, everything goes, right? Make sense? So now you have to pick, or you can come with your own idea about your quantum gravity theory. So which quantum gravity will you pick? Can I ask this question to the audience? Imagine that you're a graduate student. Tomorrow morning you have to pick some quantum gravity to work on. Which one would you pick? Well, you have to commit the next 20 years of your life on that. It's a good question, isn't it? After all, you're the future, right? We're old, but you're young. So you have to pick one. There are tons of them, right? Maybe you work on 2 of them, maybe you work on 3 of them. But later you cannot work on all of them. And given the current status of, I cannot tell you which one is the right theory to work on. Some are more explored than others. Clearly superstrings has been actually the ones that has by far been the most explored. But I guess even the most stronger believer in superstrings will probably tell you, well, we don't really know that this is the right theory. It's a nice idea. It's very consistent. But to date, we have no understanding of which actually way to go. And data that aren't enough to single one from the others. Make sense? So I would like to actually consider more a bottom-up approach. Perhaps black holes are very simple quantum systems, right? Let me just look at black holes because those are solutions of gravity, okay? So let me just think about how would I think about it. So if you actually look outside a black hole, that's all you can see. So far, we cannot peer inside the abyss. We can just effectively get close to it. So what you can say that the black hole can be viewed as a quantum system with A over 4 Gn. If you look at the dimensions, so Gn is the Newton constant, A is the area of a black hole. This cancels the number of degrees of freedom of the system. And you can say they evolve unitary under some time evolution, okay? Remember, the Newton constant can be written as the Planck-length square. So A over 4 Planck-length square is actually a number. So the central dogma tells you that, okay, but perhaps the actual black hole is a bunch of quantum states, think of it of atoms, that are strongly coupled, they confine. So it sounds a little bit like QCD, okay? And all you can see is an emergent gravity coming outside. This is actually, you can see that there are a lot of similarities to what happens in actual string theory. But it is an idea. Now, this is a beautiful idea, but it doesn't really tell you how to calculate either, right? Unless you have, again, a model like string theory. So this is another kind of emergent gravity, where gravity itself comes from a non-gravitational system, right, of a bunch of atomic states or quantum states talking to each other. So let me approach the problem in an agnostic way. Agnostic means I don't want to take any side. I don't want to say string theory is correct. I don't want to say asymptotic safety is correct. I don't want to say that is correct because I don't know. But can I make any progress on that? Because if I cannot make a progress, then it's useless. And I would like to make progress in understanding, at the very least, black hole physics, going away from the classical limit. Does it make sense? This is actually what I would like to do. It's going to be agnostic, but hopefully effective. Now, we do this already at the standard model level. If you don't want to commit to a specific extension of the standard model, you actually write an effective theory that incorporates your ignorance of the potential high energy completion of the standard model. It's not always very effective, but you can actually buy something out of it, which is as much as possible model independent. I cannot solve quantum gravity, right? I cannot deal with all of it. But at least I can try to exploit the symmetries of black hole, their asymptotic behaviors, and try to derive general results. So I would like to use black holes as quantum lampposts and eventually try to learn about the underlying theory of quantum gravity, perhaps in some experiments, or theoretically, we'll see soon how this works. Any questions so far? Is it clear enough? Since I don't hear questions, I assume this is crystal clear. I mean, this was the, if you want, the easier part, the part that actually will make you understand where I come from and what I would like to achieve. So in a series of papers, we have been building up an effective metric descriptions of quantum black holes. Okay. And how this works. Let me just go back to the ordinary Schwarzschild properties. Okay, so you can very much derive a great deal about Schwarzschild without ever looking at the Einstein equations. You know, it must be a static independent metric. It must be spherically symmetric. These are all the symmetries that you have to have. Now, if you look at the asymptotic behaviors, it must be flat at large distance. It must have an event horizon. And if you allow that to be a solution of the Einstein equation in vacuum, then you also prove that there is a singularity at the origin. Not only that, but the metric must have a specific form. But if you don't rely on any Lagrangian, but you still rely on the fact that you want a static, a spherically symmetric metric, that you still have a flat space at large distance and an event horizon, not necessarily singularity, then how would you actually write this metric? This is the most general metric you can write. This has been known since a long time. For a spherically symmetric, now you see the spherical symmetry is encoded here. Z is the radius normalizing Planck length, so it's dimensionless. And you see that it's because it is actually spherically symmetric, there are no prefactors in front of the Z. The two functions, one in front of time a 1 in front of space, so h and 1 over f, are in general not equal. They're equal only for solution of the Einstein equations, okay, in vacuum, or presence of a source at the origin of space-time. So, and the fact that it's time independent is including the fact that neither h nor f depend on time. This is the most general metric you can write, which is spherically symmetric and static. In fact, it describes also stars. A non-rotating star must have also this form. Okay. Now, let me write f and h in a slightly different way. So, with two functions, right? One in red and one in blue. And if the two functions are equal to 1, so e to the phi is equal to 1 and e to the psi is equal to 1, now you have the Schwarzschild metric, and where chi is m over m Planck. Okay, so this is actually your ordinary Schwarzschild metric. Now, nota bene that I have written these two functions as a function of a physical quantity. I can always do that. But if I do, now I win big, because my metric is exactly the same transformation property under space-time transformation as the original Schwarzschild metric. This quantity here and this quantity here will not change under metric transformation, because d is my physical distance. The physical distance from the origin, for example, is defined by just integrating your metric, right? Make sense? We have proven, but I'm not going to do that for you because it will require much more time, that you can always replace this physical distance with any other physical observable. Could be the Ricci scalar, could be the Kretschmann, could be anything else. And there is a map between the metrics written in terms of new physical quantities. Okay. I will show you the power of this in a second. But this is all the point. I can write a metric which has the same property of the Schwarzschild in terms of transformations, but the corrections are written in terms of physical quantities. And when I write in physical quantities, I have actually an insane number of constraints that I can rely on. My biggest, if you want, my biggest assumption that wherever is your quantum gravity theory that tells you how phi epsilon a it still admits a metric. If your quantum gravity does not admit a metric, then you cannot map into this. But if it doesn't meet a metric, then good luck in describing a black hole. Make sense? This is going to be insanely hands-on. I mean, you can work on this and you can get actually very interesting results. Now, the question is, going back, you see that my f depends on this quantity here, that depends on the physical distance, but the physical distance itself depends on the function f. Now, so this is a highly non-trivial self-consistent set of equations. Nothing comes for free. So the question is, how come this wasn't done before? It was tried. People even tried but failed. And the reason why they tried and failed is that this is a non-trivial, non-linear set of equations you have to solve. You cannot solve them globally, otherwise I would have solved gravity, right? Quantum gravity. But you can solve it at least locally in certain patches of space-time. Does it make sense? Again, f depends on d and d depends on f. So I have to find a way to solve this relation non-trivially. Good. So what are the natural regions I can explore? Well, if you go at very, very large distances, you have asymptotic flatness. Your d actually approaches z, and I can try to expand in 1 over d. If you are close to the horizon, then you can start expanding in the so-called Riddler space coordinate. which is a physical coordinate. And I will concentrate most on these, even though we have solved both regimes and find a number of non-trivial constraints in both cases. Make sense? Now we'll actually show how actually can solve non-trivial for these constraints. Now, if you have a way to patch together these two asymptotic regimes, then you have a full metric, okay? But then it's going to become more model dependent. So let me just concentrate around the origin, right? Sorry, around the horizon. So around the horizon, I can expand both F and H in Z. We have explored different potential expansions. I'm giving you the simplest one, but we have done our work. And because it has to have a killing horizon, you know they must start as Z minus ZH. Okay. Now, F1H means the derivative of F at the horizon. F2H means the second derivative of the horizon, and so forth, so on. Rho here is the physical distance measured starting from the horizon. DH is the physical distance from the horizon all the way to the origin. And the sum of that is your physical distance that I was calling before a little d. Good. So what is going to happen is that I can expand both the coefficients. Remember, if I go back a second here, this coefficient here and this quantity here, I can now expand them in terms of my physical distance, okay? The coefficients psi n, once you expand something in terms of physical quantity, the coefficients are also physical and no longer dependent on the way you actually change your space-time. And we'll learn also for other reasons, for example, studying the conformal window, that in quantum field theory, that once you do an expansion in physical quantity, and then the expansion is much more convergent than the one not in terms of physical quantities. Now, you immediately see that when n is equal to 0, this is just your Schwarzschild Schwarzschild coordinates. So I have two functions, right? So I have two sets of physical coefficients. These are going to be the physical coefficients that your experimental colleagues will have to fix. The values of these, xi and theta, they tell you which quantum gravity you have. Make sense? So all your ignorance about quantum gravity is now encoded in these coefficients here. Make sense? It's very simple, right? And I never had to go through the equation of motion. I never had to write the Lagrange. That's the beauty of it. I just parameterize directly the solutions. And this is exciting, at least to me. All right. Now I can go back to this expression and solve it, because I know F. I've written in terms of these coefficients, right? How do I find it? Well, I actually find first I can write rho by putting inside F the expansion I just gave it to you, and you find that rho starts with square root of Z minus ZH. And now you see that I can write Z as a function of rho. Z is my original Schwarzschild coordinate. Or I actually can write it directly as rho as a function of Z. Okay, I can invert that. Locally, I can invert that. That's a success. If I can invert it, then now I have F of rho, but F of rho is now directly written in terms of physical quantities. In ordinary classical gravity, all the other terms are 0. You only have this. This is Schwarzschild with F1, which is predicted, right? So this one are all 0. But in a generic gravity theory, I will dare say, quantum gravity, these other terms will not vanish. And that's where you get all the new physics, okay? Are you with me? Does it make sense? It's simple, right? Right. Let me calculate physical quantities now. So let me, again, as you can see, I'm getting more and more excited. I can now start calculating physical quantity at the horizon. So this is R written in terms of F and H, this and its derivative, but now written directly, I can rewrite this F and H directly as a function of rho. And the first thing that we discovered, to our surprise, is that F1 actually is singular in 1 over rho. But it shouldn't be, because the Ricci scalar is well defined. At the classical level, it's actually even 0. Schwarzschild is a theory for which the Ricci scalar is automatically 0. Okay. But this can only be 0 if the first derivative of the phi at the horizon, and this now derivative means respect to the physical quantity, it vanishes. Or in terms of this psi, if psi1 is exactly equal to 0, you can show that the same is true for the h function, so also theta1 must be equal to 0. So from requiring that your physical observables are well defined, you find 2 universal conditions on the first, exactly the first terms of the expansion in rho. Psi1 must be equal to theta1 must be equal to 0. Now I don't care which quantum gravity you have. Whichever quantum gravity predicts a metric, if this is an actual black hole, these 2 parameters must come up to be 0. Make sense? This is now a universal constraint, and now you see the world of universal description of quantum black holes. Because whichever quantum gravity you have, it has to be 0. And if it's not 0, you are not describing a black hole. And I will show you an example where actually people have written black hole metrics, but they actually were not describing black holes. So it actually has an impact. So I'm not going to bore you with the details, but you can show that you can have a number of constraints for the feasibility of a black hole, of a quantum black hole, or actually any black hole that comes from a deformed gravity. And these are the conditions that make the Ricci and finite and bounds for the positive metric function. The metric function f and h have to be positive. So you cannot have complex results. So you immediately see that C2, theta 2, psi 3, theta 3, xi1, theta 1 actually are related in a non-trivial way. Omega bar is this particular expression. So I will dare say that these are now universal constraints for physical quantum metrics. Whatever quantum metrics you actually have, it has to satisfy this. If it doesn't, then you're not describing black holes. So what that's going to learn? Well, let me go. And could you also tell me how much time do I have? Is there an answer?
Maybe the time is almost up.
Okay.
Maybe
so let me just.
A few more minutes. Just
all right. Very good.
Then
we can continue next time. So that's okay. So let me just say that if you look at the Hawking temperature, right? So in a classical black hole, Schwarzschild black hole, the temperature is inversely proportional to the mass of a black hole. The black hole actually evaporate very slowly because they go like with the mass of a black hole. So only smaller black hole, like you can see the temperature like the inverse of a mass. The smaller the mass, the higher the temperature, the faster they evaporate. So the time it takes for a black hole to evaporate is about 10 to 67 years in unit of the solar mass. So if you have an astrophysical black hole with 1 solar mass, you will never see actually evaporating. So you need very small black holes, right? ideally smaller than asteroid-sized black hole to see their evaporation. Nevertheless, this is an interesting property, and it's defined via surface gravity. So how do you calculate? One way to calculate the temperature of a black hole is to calculate surface gravity, which is written directly in terms of the first derivative of the metric at the horizon. And you can derive it directly by recognizing that the square of the surface gravity is proportional to the derivative of the time like kilometer. And this is actually the expression that you actually get, okay? If you allow me now to write in terms of the universal metric, then you find that the Hawking temperature gets modified to a quantum version of it, and only depends on three physical parameters. Originally only depending on one parameter, the mass of a black hole. Now it depends on only three physical parameters, which is the quantum horizon and the parameters specifying the underlying any quantum black hole will actually only depend on three physical parameters of the horizon. And this is actually what you learn from this expression. So I will actually stop here, maybe continue on the entropy next time, and how this relates to the temperature, if that makes any sense for you.
Okay. Yeah, thank you much. Thank you.
Yeah, you're welcome.
Let's thank Professor Sannino for the very interesting talk. Any questions? We have this.
Hello, Professor Sannino. Can you hear me?
Yes, I can.
I have a naive question. So, about your effective quantum metric of black hole, so why there is no quantum correction to the spherical directions, only in the time and the r radius direction?
Yes, this is actually, it's because it's protected by symmetry. When I say spherical symmetric, you can see the only two functions that you can have, which are general in front of the time and space, but not in front of the spherical part. That's protected. As long as you say, this is a theorem, as long as you say it's spherical, it's time independent, and then actually the coefficient in front of the spherical part is always fixed, no matter what theory of quantum gravity you have. I don't know if that answers your question, but this just comes from the fact you have.
Okay. Thank you. I'm just thinking about maybe if we have a real quantum gravity theory, the spherical parts maybe have some massive mode to fluctuate. So, yeah.
Yeah, but then you will be violating. So then you'll be violating the spherical symmetry. So.
Okay, I see. Okay,
then it's actually so you can classify. So, but for example, a paper coming out now on the generalized three-dimensional BTZ black hole, which actually also rotates, and for these there are also corrections to that. It's very exciting.
Right, but
you can even discuss the origin. Exactly.
As you said, true quantum gravity doesn't have any global symmetry. Do you still expect?
Yeah, in that case, right. But so in that case, if it doesn't have any symmetries, then it will be very hard to do actually anything. I mean, okay.
Right. Okay. Any more questions? Okay. If not, let's thank Professor Sannino again.
Thank you.
Thank you much, Francesco. Nice talk. We'll see you tomorrow. Thank you.
Is it on Wednesday, right? My next time is Wednesday, I think.
It's the same time on Wednesday. Yes, Wednesday.
Yeah, but I think it's Wednesday. Yeah.
Wednesday.
All right.
Yes.
Thanks.
Okay.
All right.
Yeah, Wednesday. So again, we need a few more minutes to prepare for the last lecture. Okay. So just plug in here.
Yeah. The key is here.
Mm-hmm.
Can you tell them that I will leave my notes available to them?
Yeah, we'll make announcement.
You just tell them.
Yeah, we'll make announcement
before.
Okay. After introduction, we'll just
Yeah,
mention.
fine. Oh, I didn't do that.
Yeah.
Oh, that's in Chinese.
No, we have another for
Yeah,
foreign.
I said that I will do it tomorrow.
Okay, sure.
And so it's 50 minutes or 1 hour?
50 minutes plus. Yeah, they're very tired. 15.
But so what I'm going to do, I'm going to do this, and then
Okay.
I will. I'm bad at that time.
Okay, I can remind you.
No, because
You can set up the clock. That's better. Yeah. So let's see.
And there is no pointer here.
There's a pointer.
Yeah, I know
There's
that,
pointer.
but it's electric. There is no
Sticker. No.
Okay, never mind. And if I do that,
This one.
Yeah.
yeah,
He
but I'm-
prefers
No.
I think I have my finger.
Oh yeah.
没事，我没有打开它的，
Otherwise,
就它的 slide 在这个
U 盘
U 盘上，
Okay.
这怎么打开
and the way you pass slides is this.
Yeah, this is pointer, the laser, and the forward and backward.
And this is
Don't touch
this
it.
is not.
Don't touch it. Only touch the
Yeah,
three
I will try.
buttons.
Usually, if you see, if you tell me that, we
Don't touch it. Okay.
like this.
It doesn't matter, but you just mess up the slides. You have to start again with some.
Oh my god.
You just quit the full screen,
Yeah.
something like that.
Otherwise, it's just the arrows, I guess.
Yeah.
No,
Is
maybe.
this-
Yeah, you try.
It's called. No, wait a minute.
No.
No, wait. No.
It's not recognized.
Can I see the folders? Okay, sorry,
Yeah.
excuse me. Click share.
Whoa. Let me try again.
So it's. So you don't see it, I think. Oh no! Wait. Is it here? Yeah, it's this one. It's. Oh no! Maybe you can. You don't need this. Maybe can I take it out?
Yeah.
So if you don't see it, it's a disaster.
Oh yeah.
It works. Oh, you know, you don't recognize that.
Oh yeah. Yeah. Right. Which one is your size?
It's wait. What happens here? When it's called Beijing something. Oh no. Wait a minute. I will find. I don't remember the name. I will find it. Because normally there are folders. Can you see the folders? in this file? Yeah. No, there are.
Oh, right here. The folders. Right.
It's
Oh,
yeah,
this one,
right inside.
Okay.
Ah,
okay.
see how organized I am.
Yeah, that's right.
Yeah, it's here actually.
Okay, I'm gonna leave the Zoom meeting.
Oh, there's a delay when you.
So you use this.
And then
change the
say I
size.
should not touch this. Yes.
Okay.
Is it the name? Is that Beijing Academy of Commerce?
No.
Should be right.
So the school is University of Chinese Media on Sundays.
So I will okay. The date, of course.
Yeah, but that's not right.
Ah, wait. You have to do it twice. See, you have to do,
Another slide.
you have to do it twice.
Ah.
If you want to go back, you see, it goes that way. But if you want to go back, oh, it's for the first one that you have a problem for some reason.
Is okay?
Yeah.
And I want to work this.
And this is what?
This
The
is my
microphone?
for the online live stream.
No, no.
Oh, is it okay?
孩子的，
对，还是能。
那一会儿给他带上吧。那我先放这儿。
啊？
哦。
哦。
Shall we start?
Yeah, yeah.
So this is a microphone.
I have one.
You have one.
Then I will say 15 minutes.
Okay. So let's start the last lecture of today's session. So the last lecture of today is Professor Laurent Beaulieu from Sorbonne University in Paris. So Professor Beaulieu is a great expert on the formal field theory side of quantum field theory and gravity. And he's going to give us 2 lectures. The title of his lecture is Bulk and Holographic Word Identities and 1.5 Noether Theorem for BST and the Batalin-Vierkovsky gauge fixed actions. And Professor Beaulieu is very kind. He said he's going to share his slides so we can distribute his slides to all the students. You can read the slides in more detail later. So let's welcome him.
So it's something that's going to be self-consistent, I hope. The thing is that there are new things here in the title, which is the word holographic word identities and also 1.5 Noether theorem. So 1.5 Noether theorem is the word we invented. It's just a tribute to Mrs. Emily Noether. And it's something that we did when we wanted to make more sense about these ideas that Strominger and his team and other people in the world have done for the last 10 years, saying that when you quantize a theory, gravity, Young-Mills, in fact, Emmy-Gauge theory, it has been known since 1 century, Emily Noether's second theorem, that if you have a gauge symmetry, so we understand very well, we are very familiar as physicists with the consequence of having a Lagrangian with a gauge symmetry, that is local gauge transformations. And then one of the greatest results of physics has been done when you were not born, and me neither, actually, when people made sense of the quantum field theory, the perturbative one that you can compute out of the Young-Mills theory in many details. But then, of course, as you know, people understood very well the problem of, I mean, what you have to do to control and master the local phenomenon. That is you have to renormalize, you have a local effect. And then the study of these very local things led to many, many predictions. On the other hand, the thing that was left aside was the effect on the
on gate theories of the existence of the global neuter charge that were discovered, in fact, a century ago, which are very well known by mathematicians and all that, that says that for a gate theory, and actually you have to be in Minkowski space, you have this phenomenon that you have an infinite set of global charges, that are called the global neuter charges, and these charges, they have a charge density that is supported by the boundary. And more precisely, it is supported by, you must have boundaries with corners. So it's something which is extremely beautiful. And what happened is that around, in my knowledge, it's only around 2014 that Strominger and other people, and of course people like Hawking and other people, they knew about that. But they were not as experts in quantum field theory as Strominger. And then the thing that I like very much is that one consequence, and that was postulated in Hamilton formalism. And then this lecture will be about Lagrangian formalism to see how it really works from the first principles of quantum field theory. And then the Strominger and company said, okay, there is something about this infinite set of global charge that are supported by the corners of the manifolds and all that, is that they have this property, which is magical from my point of view, which is the fact that they have to commute with the physical S matrix if you have a gate theory. For me, it's a very important theorem because it says that when you quantize a gate theory, not only you have the constraint of gate symmetry, word identities, and all that, but also you have to find a way to compute the S matrix in such a way that at the end of the day, the S matrix will commute with all these global charges. Okay? Now, that's magnificent. And if you go a bit further, you understand that, you see the global charge are located on the boundary, on the corners of the boundary. It's Lorentz space, so you have an S matrix. But then you have also to understand that the S matrix is a kind of map from the boundary. So it makes a lot of sense. And in fact, somehow, as soon as you start to put that in your head, you say, aha, okay, but that's something like the Weinberg theorem or the prescription that you use. The S matrix doesn't exist. You have to compute these so-called amplitude physics where you have soft photons and all that. So, in fact, when you take care of what happens at the boundary, you start to realize that you have to really understand what's going on, and then it has to come in a natural way that what you compute at the end is not only a so-called S matrix with unshelled particles, but each unshelled particles, you have to put soft photons and all that to correct the infrared problems. Now, with this asymptotic, this holographic word identity, which cares about what happens at the boundary, then you have a constraint, and this constraint tells you that the S matrix must commute with the global charges and all that. And at the end of the day, you get the prescription that was discovered in the 30s, 37, when people discovered the way to compute not the S matrix, but the scattering process of particles with clouds of soft photons or soft gravitons and so on. So I think it's a very interesting thing. And then I got very interested by that. Young people, when they work on that, they find it's very new. Now, the 1.5 theorem is just the fact that and now this scheme was predicted by Strominger. People did a lot of things, but it was always at the classical level, no gate fixing, okay, and in Hamilton formalism, which is nice, but that's not the way we compute. And then the trick, one question that you may have at the beginning is that this very beautiful phenomenon that the global charges commute with the S matrix, okay, when you do computations, you have to organize your computation by working in a given gauge. For instance, Landau, Feynman, whatever, in the case of Young-Mills. In gravity, since it's far away for the graviton, you take the Bondi gauge, okay? But you could also play the de Donder gauge and all that. And one of the first questions I was asking to Strominger when he was lecturing in Cargès is, what happens when you change gauge? And of course, they didn't know. And moreover, in Hamilton formalism, you don't really know how to organize your computations, you see, to compute amplitudes. So there was something to be done, and at the end of the day, it's kind of simple. Okay, now this. See? Right. Then, you see, first of all, you will have there are many transparents. I don't know how time will fly, but you will get the things, right? And then what happens is actually very simple. And when we, including me when I was a student and after and all that, you see, when we do computations in perturbation theory for scattering, for graviton, when you do one loop corrections to gravitation in a flat ground and all that, and when you do more things on the Weinberg-Salam model and all that, you see, you have to take care of the gauge symmetry, and you always have to fix the gauge, right? So the question that you may have is the following. Mrs. Emily Noether, when she discovered the second Noether theorem for gauge theory, of course, she didn't know Young-Mills. She was playing only, which is, of course, a lot with gravity and electromagnetism. And at the time, people would not think about gauge fixing because gauge fixing was obvious. At the classical level, when you solve equations of motions, you can brutally fix the gauge and you solve the equations of motion in this gauge, okay? But then, of course, when you try to quantize, somehow you go off shell, you do the path integral or any other method, and then it was very quickly discovered that fixing the gauge in theory which are gauge theory which are not so trivial, with some gauge functions like the Landau gauge in QCD or QED and so on. Then what happened is that you need other fields, ghosts and all that. So it's very clear that the second Noether theorem, that is a classical theorem, and says that you have these global charges that are supported by the boundary when the fields don't vanish at infinity and all that, but they decay slowly, like 1 over r squared, for instance. Then you play with equations relying on the gauge symmetry of your Lagrangian. But at the quantum level, when you compute, you have to fix the gauge. So the second Noether theorem has 0 value at the quantum level, right? So when I was asking the question to Strominger, of course he could not answer because he was supposing that the global charges would be the same at the quantum level. And actually the global charges are like everything else in quantum field theory, where you have renormalizations, they get modified by the corrections, right? And then you can say, then the question that I told him, but then you don't have any warranty that what you compute, for instance, in the Bondi gauge for gravity will be the same as in the Donder gauge. And of course, he said, yes, we don't know. I'm going to explain how you define the global charge in for And by the way, the S matrix itself, there is no S matrix at the classical level. Okay, you have to. S matrix is a purely quantum concept. Okay, some points you can say, well, a particle is like a pen wave and all that, but it's not enough, right? So in any case, when you compute, for instance, this theorem that the S matrix commutes with a global charge is very non-trivial because the global charge of Mrs. Noether are purely classical, and the S matrix is by definition totally quantum, with all subtleties of quantum field theories like soft particles and all that. So the idea, of course, was to say, take a gauge theory, gravity or whatever, then fix the gauge, do it as it should be done in such a way that you have, at the end of the day, something that you call an S matrix, which is unitary and gauge independent. So you have to go through this so-called Biresti formalism, or Batalin-Vilkovsky formalism, that is extremely well known now. And then you have more fields. You have the classical fields, you have the ghosts, you have the Lagrange multiplier to do the gauge fixing. And then you have to see, but what happened to the second Noether theorem? Because you have fixed the gauge, you don't have a gauge invariance. So that was the exercise that we were lucky enough to solve. Okay, and what is in blue? See, after this thing, there will be technical things, but there are a few ideas that should remain. And then the idea is very simple. You see, that's in blue here. So we will show that, of course, when you quantize a gauge theory, you break gauge invariance, but as you know, you introduce ghosts in such a way that the effect of the propagation of unphysical particle is compensated by these ghosts. That's how Feynman invented the ghost in '62, something like that. But he didn't ask himself the question, but okay, I introduced ghosts to compensate for the unphysical modes that propagate due to the gauge fixing, and they have to propagate because otherwise my path integral is just not defined. The propagator is not invertible and all that. So you have to define the propagation for unphysical modes. And then Feynman said, okay, then I have to, he was doing that for gravity actually, not for Young-Mills, but he took Young-Mills, SU2, as a toy model. You see, it was before people understood that Young-Mills was so physical. And then he said, okay, the ghosts, they will have loops exactly as the gluons say, and then they will have odd statistics in such a way that their loops will contribute with opposite sign to the contribution of the unphysical particles, and so on. He had all physical ideas. It was deeply correct. Then, but he didn't ask the good question, how the gauge symmetry is going to act on the ghosts. And in fact, the point is that there is no gauge symmetry acting on the ghosts. The ghosts are just unphysical. They don't care about the gauge symmetry. But then what happens is that you have to do this exercise that the loops of the ghosts have to compensate the loops of the unphysical particles, the longitudinal bosons in the W or mu or gravity nu, etc. And then he should have said, but in order this compensation to be valid all the time, okay, loop by loop, zillions of loops, it has to work. And then there should be a symmetry that relates the ghosts and the classical fields. But at the time, you would say, but that's impossible because the ghosts have negative statistics, actually the opposite of the classical fields. And then how can you find a symmetry? And then people had only a formula by Dirac saying with determinant and all that. But at the end of the day, you get a Lagrangian where you have a symmetry. The Lagrangian is not gauge invariant anymore because it's gauge fixed, but you have a symmetry, and this symmetry was discovered in '74 by Becky Rouet and Stora. who just read what was the Federer-Popov Lagrangian in the Landau gauge. And they had this very good idea that because Tufte had understood that you have word identities for this Lagrangian that he guessed in a marvelous paper in 71. But then Storer said, in order to get these word identities, you must have a symmetry, and in fact, a global symmetry. So what happened is that the gauge fixed Lagrangian, when you put the ghosts according to various ways to do it in a consistent way to get word identities, then this Lagrangian has no gauge symmetry, but it has a fermionic symmetry that relates the ghosts and the classical fields. It's called the Beerès symmetry, and it's a global symmetry, right? So you lose the gauge symmetry acting on the gauge field, but then you introduce more fields, and having more fields, you have more infinities, and then you just need a global symmetry, which has less degrees of freedom. So now it's a button. Right. And then observe, and then as soon as you got this in your bones, that you replace the gauge symmetry by a global symmetry, and that it gives the word identities that know everything about the gauge symmetry at the quantum level, you say, well, it's very easy to do that. I'm going to use the first Noether theorem for a global symmetry applied to the Beerès symmetry. Okay, isn't it trivial as a goal? And the big surprise for me was that that was done 2 years ago. You see, people like me, I was educated by Raymond Storer and so on. We had this way to look at gauge theory in perturbation theory, gravity, etc., and moreover in the Euclidean space. And then we were only interested by things like anomalies, renormalization, that are short distance phenomena. Okay? And then you will never see, at the classical level in an Euclidean theory, you never see, you don't see the global charges. Because in order the global charges to exist, you need a manifold with non-trivial boundaries and moreover boundaries that have corners. And that a phenomenon which is known at the classical level. And then for most of the people who were concerned for gauge theories about ultraviolet problems and all that anomalies, you don't care. You're in Euclidean space. And moreover, when you do computations, most of the time you go to the Euclidean space and you play with the Wick rotation. Okay, now the Wick rotation is something very fantastic. It's a property of Feynman diagrams. No one knows if it has a non-perturbative meaning, and so on and so on. But that's the way we were educated. And it was the fundamental question. I believe it's a fundamental question, which is to say, when we quantize a gauge theory, we have to impose at the quantum level that the Beerès Noether current is conserved. It was never asked. Okay. Now, and then when you play the role, you will see that now not only you have the word identities for the bulk, as in the past, you know very well how to impose what I call the bulk boundary word identities, or the BV equation. It's a nonlinear equation. It says that the bracket of the effective potential gamma is 0, and if it is not 0, it is an anomaly. If it is an anomaly, you cannot impose gamma equal to 0 order by order, etc. The Green-Schwarz mechanism, all that, we're totally coded for that now. But then there is another one, which is a word identity, which is on the boundary. And what's going to happen is that at the quantum level, if you look at the Noether current for the Beerest symmetry of the Beerest invariant Lagrangian, you will get a current that has to be conserved. And we have a proof that we call 1.5 Noether theorem, because it's between local and global. It's a little joke. It's just the fact that, in fact, this word entity is just one for a global current. And then we prove that this Noether current, in general, for a large class of theory, we have a generic formula. This Noether current, that is conserved on shell, is locally everywhere on the boundary and so on. It's D-exact as the classical Noether theorem, plus an S-exact term. It's a very non-trivial computation. And then it defines a charge. So this charge is basically the classical Noether charge plus a term, which is S-exact. Now, if you take the commutator of this charge with something physical, because the thing that is physical is in the cohomology of the Beerest symmetry, you don't care about adding an S-exact term to a charge. So at the end of the day, you prove by your word identity that indeed, when you do perturbative computations, the very old Noether charge, infinite number of them, but computed in a different way, has to commute with the S matrix. Right? And the beautiful thing is that then you find a constraint on how you define the S matrix, what you call the S matrix, and then you have to put the soft photons and all that. So I find it fascinating how lazy all my colleagues, including me, we have been for decades. It should have been done first. Something was missing. See?
Nobody derived the BRST?
No, because people, the thing that it's a matter of communities, you see. The people, because you see, I'm going to talk about the Mondi. I mean, there are many things you will be able to read the transparencies. You see, what happened is that in all this work, I think the pioneer was Bondi and his people, beginning of 60s, and actually Penrose too. Because in order to make this, I will show a Penrose diagram that says a lot about what you have to do for. I mean, there are many things. These little remarks, they have many ramifications. But then you see the point is that when you look at the papers of Bondi and company, you know, they were interested indeed to what happens at the boundaries with the BMS symmetry, okay? And they never talked about ghosts. You see, they had parameters and all that, and they were playing with Hamilton formalism. And actually, the people doing gravity, especially at the time, but of course, De Witt, in a sense, invented the ghost. But even if he invented the ghost with Feynman, he didn't think to that. And he could have done it, okay? But they didn't do it because they don't really care about gauge fixing. No, but still, they should, because you see, for instance, the way to choose a good system of coordinates is a gauge fixing. But the way you use this freedom of the theory, which is like fixing a gauge, is not considered as a gauge fixing. And then they don't say, yes, but if I choose something too complicated, I will have ghosts that propagate. See? And then you have to care about the interaction of the ghosts. And Polyakov was fantastic because he understood that in 2 dimensions, when you go to the conformal gauge, the ghosts contribute to the central charge, to the anomaly. You get D minus 26. The 26 is from the ghosts. Okay? You get critical dimensions. You need people like Polyakov to combine gravity and quantum things. Okay? And by the way, something that is important, you know, I was talking about, then you see that in quantum theory, there's a big difference between Euclidean and Minkowski. And I remember that once Polyakov told me, because I was asking him some other questions, he said, Polyakov doesn't believe that you can define a quantum field theory for gravity in dimension bigger than 2. Then he says, probably it exists in Lorentz space, but not in Euclidean space. And then, what does it say? It says that in gravity, if you do things non-perturbatively, or I don't know how, you will get nothing like the Wick rotation. So the Wick rotation is a peculiar, I believe that the Wick rotation is a peculiarity of computing Feynman diagram, obviously. Okay, they have analyticity properties and etc. So it's clear that they are formula. So you cannot rely, and it's a good example. The case of Noether global charges is very interesting because you don't care about them in Euclidean space, and you do care a lot about them in Lorentz space. And also they have to do, you see, these global symmetries, their role, that's now I'm convinced about that, is to give you a proper definition of the S matrix. The S matrix has to be invariant under the Noether global charge. That's the definition. Okay? But you don't have an S matrix in Euclidean space. So it fits. See? I think I'm going to spend all my time discussing. And then, yeah. Okay, so that's the idea, and that's the result. We have a formula. So up to now, we know what is the we can easily compute, because you have a general formula, this Noether current and the associated word identity for all gate series that are called rank 1 Batali-Vilkovsky system. That simply means that, of course, you have a Lagrangian. It has a symmetry, a gate symmetry. But this symmetry, if it's rank 1, close off shell. Okay? If the Batali, and then, so we have this series, Young-Mills, Young-Mills, gravity, diffeomorphism, supergravity, many series that involve two-form gauge fields. We stop at rank 2 for the two forms because we could do it, but it would be more difficult to prove the theorem. So we have a general formula, and that says we know the constraint on their S matrix, if we're interested by the S matrix, and the S matrix is the improved one with soft particles and all that. And for the moment, we are working, but we are convinced that it will work for BV system of arbitrary ranks. So at the beginning, when I came here, I was thinking that I would talk about this, but I think it's more fun to talk about what I'm talking now. Okay. Aha. I do.
On the computer.
At the computer, yeah. Sorry. Okay. Then, yeah, something else that you will see, and maybe some people are interested by that, people who like Hamiltonian framework, they have a notion which is called the covariant phase space. You see, if you like, and if you like mathematics and physics at the same time, it's useful to learn about these things, because the concept which is at the basis of what one calls covariant phase space in quantum field theory is the fact that one takes very seriously the space, the manifold, where each point is a field configuration, right? And then when you do the path integral, you sum over field configurations. So it's very natural to define the path integral, because when you do the path integral, you have a measure for each field configuration and you sum over all that, right? So the so-called covariant phase space is a nice concept. It is interesting if you teach physics or you want to learn physics, because you see what happens is that you generalize the notion of a Riemann manifold where each point is a point, so it's finite dimensional. But then you say, okay, I can say that one point is a field, okay? But Riemannian geometry, you have the point, and then you have tangent space. So you define the dx mu, which is a one form. And then you have p forms. And so you have tangent space, and you have a differential geometry. And then you can define what is the variation of, so the variation of a field is a delta phi, right? But then, in the same way that you have vectors in the space of point, which are basically dual to the differential forms, right? Then, in the covariant phase space, people who are totally like alcoholic about that, and you see, and then in the same way that you have a Lie derivative, you can define a Lie derivative along a vector field in a Riemann manifold. Then you can define some vector field vector fields for vectors and so on. So you get a nice picture, okay? But then what happens? So at the classical level, it's something which is very well known. And actually, many people who have been working on global charges, they use this concept of covariant phase space. My belief it's a bit, their interest is a bit too exact because you get lost, because it's very difficult to visualize this space. But then, you see, what happens is that at some point you say, wait, classical things are limit of quantum things, but gauge theory, we believe that they are important, but we, as physicists, we only play with infinitesimal transformations. It's not much, okay? And mathematicians, I've been working with some good mathematicians, and for them, they were very frustrated because we basically only care about small things, infinitesimal gauge transformations. But you see, what happens is that when we quantize, the difficulties that we encountered forced us to abandon the notion of a gauge transformation, a small transformation. We passed to the B-res transformations. So, and where can we do that? You see, in a sense, we reduce the size of the symmetry, because you pass from a symmetry where the parameter is local to a symmetry where the parameter is global. Actually, it's an anti-commuting number. It's only one parameter. It's a constant parameter, anti-commuting. But we add the ghost fields. So we add many more degrees of freedom. And moreover, you take as a principle the fact that physics don't depend on the ghost fields. In fact, physics is defined by the cohomology of the B-res symmetry. So somehow you see, the infinite degeneracy due to the gauge symmetry and represented by something that mathematicians don't like because it's an infinitesimal gauge transformation. When you go to the gauge fixing, it becomes a global symmetry that you can explain to a mathematician. He will even say that the gauss gives a name, and so I mean there is a whole formalism before that. And then, so the only thing that you have to do is to have a phase space, so a covariant phase space. I call it a B-res covariant phase space, where the points are made of field configurations for the gauge fields, for the classical fields, for the gauss, for the anti-gauss, and for the Lagrange multiplier. It's good, it's just a bigger space, okay? And then in this space, so you can define what is the variation of a gauss and company. So you give exactly the same status to the so-called physical and physical fields. And then, of course, you say, what is the definition of physical and not physical? Well, physical things, observable things, are the cohomology of this S symmetry. That makes sense. Okay? So at the end of the day, you will say, okay, I don't care about the C, the anti-ghost, the B. The only thing that matters are the, say, transverse, if it's electrodynamic, the transverse photons. But then, you see, a physical state is defined modulo the addition of an S exact term. So for a mathematician, it's perfect, and actually for us too. Okay? And at the end of the day, you have a big space that has a BRST covariance, which is well defined. You define physical things. You define a BRST invariant since you know what is the variation of a field. You just introduce the measure of the path integral, which is delta A, delta C, etc. And then you find a way, you invent a calculus, as Riemann did, to compute C number by path integrals. So it's a beautiful framework. And you don't have to fight with these things like infinitesimal transformations. You don't know what is you don't know what are the big transformations, and so on and so on. Of course, you have transformations that are not connected to the identity. All this can be reformulated. Okay? So in any case, what happens is that everything that you have to compute to have control of the global charges takes a kind of, it becomes transparent, and then you understand that your BRST covariance space has a tree grading. It's a tree graded space where, and what happened is as follows. You see, you're playing with mathematics to compute some integrals, and you have various operations. You have differential operators. So the first grading is the fact that you have the dx mu for the coordinates. It's clear that you're grading dx mu is anti-commuting, dx mu is, and so on and so on. You have exterior products. Okay? So you have one direction that defines the grading, which is dx mu. Then you have another direction because it's a covariant phase space that is given a point which is a field configuration. You know what is the variation of the point. You call it delta phi. That's what we call a variation of the trajectory when we do the path integral. So we have another guy, a second grading is by delta x mu. Now, the big grading of covariant phase space has been known for a long time, and it was made of dx mu and delta phi. Many huge papers on that and so on, but we know exactly what it is. It's for scalar field theory. But then the third grading is going to be the BRS symmetry, because we have fields which have Gauss number. We have mu, which I take mu. Mu has Gauss number 0. C has Gauss number 1. C bar -1. And the Lagrange multiplier is like mu, it has Gauss number 0. And then it defines a third grading. But this grading is very analogous to the other ones. So you have d, delta, and s. D squared is 0, s squared is 0, but s squared equal to 0 is equivalent to the fact that you have a Jacobi identity and a closure relation. Okay? So it means something. And delta squared equal to 0 is the fact that indeed you can say that a field trajectory can have a variation, and it's a differential. So if phi is commuting, delta phi is anti-commuting, right? And then you develop some calculus rules, which are whatever they are, and you're very satisfied. And at the end of the day, when you write a path integral, you clearly see that you have an object which is a measure. You have a Lagrangian which is invariant. You know that what happens to the action when you add a topological term, d of something, okay? Because d squared is equal to 0. When you add s of something or something analogous, you do something, and at the end of the day, you understand that it's a gauge fixing, and so on. And then I'm remaking the history. It took many decades to go to there. And at the end of the day, you say, okay, the physics is going to be defined by computing the correlation function by path integral or an object that is in the cohomology of S. Okay, and you have an easy theorem that says that if the measure of the path integral is S invariant, then the mean value of an object which is S exact is 0. See, and you get all the material that you need to do progresses. And so it's not surprised that at the end of the day we could generalize at the quantum level the Noether theorem. See? Now you see, no, we can even stop because there was a second one, and then I will give more technical things. Okay, sure. I think it's much better to have the general ideas than see.
Less than 10 minutes.
Yeah, but it's okay. So let me go on. And now I don't see the same here and here. Yeah. Then okay. So right. So I talk at length about this Biressi covariant phase space, but it's really a good guideline. And then I just say that for me it's kind of a sect. There are people who say there is something that we call canonical quantization. And then I must say that I never understood how you can compute anything in the framework of canonical quantization. They define some charges, something, and so on. But they rely on this thing. But I think they miss the point of path integral. So I believe that existence of covariant phase space, especially the Biressi covariant for gauge theory, is very suggestive because it gives you the intuition of what you can do and cannot do in quantum field theory. Okay, so, and then, so, that's what we will prove, this word identity, which is the fact that this equation, where these are the Noether charge computed for the Biressi invariant action, so that defines what is the S matrix, okay? And it says that the S matrix has to get rid of infinite properties. So in a sense, you see, we get a word identity which helps to master the infinite questions in perturbation theory. Exactly as the old Biressi word identity that is based on the Biressi symmetry in the bulk at short distance is the identity that allows you to master the difficulties due to the ultraviolet problems. Okay? Now, if after these lectures you keep that in your mind, it's fantastic. Because after that, it's your own work. It takes time to become familiar with that. Okay? So then also a picture that I will not use, but it is very important, and it reminds me what I heard in the last talk. You see, this is, you see, you have the thing which is very difficult. Everything I said is abstract, but it resonates if you understand the physics. And you see, the physics of the S matrix is something that we don't really understand. Because okay, scattering particles, but what is an S matrix is not at all trivial. Okay, the reason is that it doesn't correspond to anything classical in a sense. Okay, these are not waves that do that. It's much more complicated. And then what happened again? You see, I love these people of the 60s: Bondi, Metzner, Sachs. And so they were extraordinary people, okay? And then their problem indeed was the fact that Einstein invented the gravitational waves, but very, very quickly until the end, he said, no, they cannot exist, the gravitational waves, because they are in flat space. And then I can always find a system of coordinates where they disappear, okay? And the point was what? And it was discovered after his death. And actually, the mathematician played a good role for that. They say, when you look at the problem of green functions for plane waves and all that, you don't treat well the boundary conditions. And in particular, Einstein wanted to have an action first principle. So he wanted to get rid of the fact that the action depends on second derivative of g mu nu, of course. And then by part integration, you get a boundary term, and the equation of motion don't see and so on. But then the point is that in Einstein, in gravitation, the effect of the boundary is fundamental, even for things as simple as the propagation of so-called free graviton. Okay, but so that was very in the 60s again. This, I mean, really extraordinary people. On the other hand, they didn't learn enough quantum field theory, and then it was two communities. Okay, and the people doing quantum field theory, they were not listening enough to the people doing gravity at the time. It was two communities. Okay, then in the 60s, the other thing was to discover that as soon as you have gravitons, you're talking gravity. You cannot say that a graviton exists in this is for you, Paul. A graviton cannot exist in a space that is flat. Okay, it can only exist in a space that has a minima a very small curvature. Okay, and then Bondi said, okay, is it possible that I have a black hole or whatever in a space where at infinity the metric is flat? Okay, and actually the answer is no. Things have to be asymptotically flat, and actually it's clear that if you have nothing in the space, you have nothing in the space. But as soon if you have gravitons, it means that somewhere you have to create something. So it's like an electric field or whatever in electromagnetism. And then at infinity, the fields are never zero. They're like 1 over r squared. Okay? And then what happens is that that's what they call a space with asymptotically flat. Okay? And then Bondi said, that's a marvel. Asymptotically, the fields can only be asymptotically flat. So the Lorentz symmetry, you never have it as soon as you have matter. Okay? And then he discovered the so-called BMS symmetry that characterize at very large distance the behavior of the gravitational field, and with a BMS symmetry. This BMS symmetry determines a matrix, and this matrix has coefficients whose intensity disappear in a certain function of 1 over r squared, right? And then you can have a leading things and so on. And this BMS symmetry is fundamental actually to understand what is a plane wave. So what he said, he solved the problem of Einstein very quickly. He said, okay, I can have gravitons coming from far away. And basically, you see, and then the paper was complicated. It was totally unknown for people doing quantum field theory. I had to wait the COVID to study that, for instance. But then you see the basic ideas. But then you see in 65 or 66, the paper is difficult to read. Okay, but 2 years after the paper, Penrose did this diagram. So what is this diagram? This diagram, this is the coordinates are u and v, tau plus and tau minus. So this is the boundary. So the space is basically flat inside. There is nothing, but you need something to interact with graviton if gravitons arrive. So a little mass or something like that here. And then this is the boundary for tau minus infinity, tau plus infinity. And then, what happens, he said, somehow, the thing that is fantastic in the universe is that for some reasons, the boundary of the universe, I mean, in tau plus and 2 minus, is able to emit or absorb gravitons that, of course, go either, I mean, those who are created, they go along tau plus, and this that is absorbed, they go along tau minus, because you see, the observer is here. So either you send a graviton that will go to the boundary of space here, or you receive one, okay? And basically, when you take that, say that by definition, at infinity, you have asymptotic flatness, then you have an approximation of the metric, you solve the equation of motions, and you have indeed the possibility that the boundary is able to absorb gravitons, and this one to emit graviton, and it is all consistent. But then what happens is that the difficulty that was solved by Bondi was the fact that this works as a machine, as a buffer, and then when you emit a graviton, you have to compensate for something. And there is a so-called Bondi mass effect. So when you emit a graviton here, something changes in the component of the metric here, but this something is like, it's called the Bondi mass effect, is that if a small mass was created here, that would provoke this. So at the end, they discovered, they were geniuses. They discovered, that's my interpretation, they discovered that if you want to move, it means that you change your mass somehow, and that's a Bondi mass effect. So when you move in order to be able to move your arm, okay, it's a gravity change. Okay, well, you do that, or it's gravitational. You fight against something, and then there is a change here. But this change is only possible because you emit a graviton here. So there is an equilibrium between a non-trivial dynamics of gravitation and emission and absorptions in the boundaries. And that solved the fact, they solved the fact that, you know, I heard that so many times, that in gravity, how can you have a dynamic with a Hamiltonian that vanishes? Okay, of course the Hamiltonian vanish, but the Hamiltonian is for the evolution along slices along t direction, not tau plus and tau minus. So they taught us, these people, and I mean, in my community, I was not born, so but people didn't listen to that. They solved the fact that h is equal to 0, and they solved the question of Einstein. That's why you can have graviton. Okay, because the graviton, you cannot cancel them. You cannot do a change of coordinates to get rid of them, because you have to fight, you have to absorb the energy. You see, the boundary is a very sophisticated object. It can emit or it's like a buffer. It can emit or absorb graviton here, but then this emission has to correspond to something. The something can be the fact that this is a gravitational wave, okay, and then it will be absorbed by a detector, okay, but then something else must happen. The detector will move, and then some kind of soft gravitons will go somewhere. It's beautiful, right? So I just want to say the following. I just want to say that if you have a gauge theory, including gravity, you better to understand to what happens on the boundaries. Okay, and now we have the good tool for that. We have word identities. Now, the technical way, I will explain how to get the word identities, but it's not the deep point. See? I mean, the work of getting this Noether, it's totally trivial to define this. You know the Beeré symmetry, it's a global symmetry. You just apply the formula of 16th century to get the Noether current. Okay, and after that, you see what happened, what are the consequences of this global symmetry when you compute correlation functions. You have word identities, and you see the consequences. Okay, but I think it's a conceptual progress. I hope it will motivate you to read the thing. Okay, and next time I will do what I can do. But you see, this, in a sense, I found this picture most interesting, and it is indeed due to Penrose. You see, and the way you get, you see the fact, you see here. So everything here is reparametrization invariance, which is a gauge symmetry. G mu, variation of G mu nu is Lixi G mu nu. So when you introduce ghosts, you have a ghost, you change psi, the small parameter, into a ghost field, exactly as you change epsilon for Yang-Mills into phi of ghost C, okay? So you change, so you not only have G mu nu, but you have psi mu, and you have a B-res symmetry. So S G mu nu is Lixi of G mu nu, and S of psi mu is psi nu D nu psi mu, and S squared is equal to 0. And then that's your B-res symmetry. Then you have a path integral. You have a Lagrangian which is B-res invariant. And then the simplest trick that you can think of is as follows. You just do a change of variable in your path integral, which is you just redefine phi, which is either G mu nu or psi mu, into something which is the same plus something small, the small parameter that depends on x, times this guy. Then you just say that it doesn't change the path integral because the action is S invariant, okay? And then you get consequences. And these consequences are the fact that, for instance, the S matrix, if you define it as you should, has to commute with the global charge associated to the S symmetry.
Okay.
Okay.
I think we.
What can I say?
Okay, let's thank Professor Beaulieu for the very profound lecture. Any short questions? Okay, maybe you can read his lecture notes first.
I think I will show you examples of how it goes on,
Okay.
on simple cases.
We need some time to digest.
No, I had my whole life needed
to educate us.
No, it's clear that, that it was a big hole that was left open in the quantization of gauge theory.
Yeah,
which was not to take into
Right.
account the existence of global.
That's right.
For in the Minkowski's case.
That's very profound. So any one of you wants to quantize gravity, you should, this is a starting point. Okay, let's thank Professor Beaulieu again. So we need to run for dinner, otherwise we're gonna miss dinner time. Thank you. Nice talk.
Next one will be when?